What if I told you that our closest cosmic neighbour, the star system we've dreamed about reaching for generations, is actually a graveyard? For over 6 decades, Alpha Centauri has been humanity's beacon of hope, sitting just 4.2 light-years away, close enough to touch by cosmic standards. We discovered planets there. We found worlds in the habitable zone. Scientists designed missions, engineers built prototypes. Millions of dollars were invested in projects aimed at reaching this nearest stellar neighbour. But then James Webb Space Telescope aimed its unprecedented instruments at Alpha Centauri and uncovered something that shattered every optimistic prediction we ever made about this system. The truth is so disturbing that it's forcing us to completely rewrite our understanding of where life can exist in the universe. And here's what nobody's talking about. If Alpha Centauri is dead, if the closest star system to Earth cannot support life, what does that mean for the rest of the galaxy? What does it mean for the billions of stars we thought might host habitable worlds? The implications are staggering, and they reach far beyond this single stellar system. Before we dive deep into these revelations, if cosmic mysteries like this fascinate you, if you want to explore more of the universe's darkest secrets, go ahead and hit that subscribe button. It genuinely helps us create more content exploring these mind-bending discoveries. Now, let's uncover exactly what James Webb found and why it changes everything we thought we knew about our place in the cosmos. When you look up at the night sky from anywhere in the southern hemisphere, your eyes can see Alpha Centauri without any telescopes, without any instruments, just your naked eye observing a brilliant point of light in the constellation Centaurus. What appears as a single star is actually 3 separate suns, gravitationally bound together in an eternal cosmic dance that's been ongoing for billions of years. This triple star system has captivated astronomers, writers, and dreamers since humans first gazed upward and wondered what lay beyond our world. Ancient astronomers mapped its position. Science fiction writers imagined civilizations orbiting these stars. Modern scientists calculated the feasibility of actually sending spacecraft there. The distance between us and Alpha Centauri is staggering when you try to wrap your mind around the actual numbers. We're talking about approximately 25 trillion miles, a number so incomprehensibly large that it becomes almost meaningless, without proper context to understand what it really represents. Light itself, travelling at 186,000 miles per second, the fastest speed possible in our universe according to Einstein's relativity, takes over 4 years to make this journey. Think about that for a moment. A beam of light that leaves Alpha Centauri tonight, right now as you're watching this video, will not reach your eyes until sometime in the year 2029 or 2030. You'll be 4 years older before that light completes its journey. If you could somehow board a commercial jet and fly toward Alpha Centauri, maintaining cruising altitude and speed indefinitely, somehow magically flying through the vacuum of space at the same speed jets fly through Earth's atmosphere, your voyage would last roughly 5 million years. Your descendants, separated from you by 200,000 generations, each generation living and dying never knowing anything but the interior of that aircraft, would be the ones to finally arrive at the destination you originally set out toward. Generations would forget why they're travelling. Languages would evolve, cultures would rise and fall, all aboard a single vessel making this interminable journey across the cosmic void. Yet in the grand cosmic scale of things, Alpha Centauri sits practically in our backyard. The Milky Way galaxy stretches 100,000 light-years from one edge to the other. Alpha Centauri lies closer to us than 99.99% of every other star in our galactic neighbourhood. The numbers here are staggering. Our galaxy contains somewhere between 200 and 400 billion stars. Of all those billions upon billions of stellar furnaces, Alpha Centauri ranks as the closest. We won the cosmic lottery in terms of having a nearby neighbour, or so we thought. Imagine shrinking our entire galaxy down to the size of the United States, from the Atlantic to the Pacific, from Canada to Mexico, the whole continental expanse representing the Milky Way. In this scale model, the distance to Alpha Centauri would be equivalent to walking across a single room in your house. Just a few steps across your living room would represent the gulf between our solar system and our nearest stellar neighbour. If the Milky Way were compressed to fit inside a football stadium, from one end zone to the other, The gap between us and Alpha Centauri would measure smaller than a grain of rice. This proximity is extraordinary when you consider the vast distances that typically separate stars in our galaxy. This remarkable proximity transformed Alpha Centauri into the focal point of humanity's first serious attempts at interstellar exploration. When scientists and engineers began drafting actual plans, not science fiction fantasies but real engineering proposals for missions beyond our solar system, Alpha Centauri emerged as the only logical first destination. The reasoning was simple and compelling. It's the closest. Any mission to any other star would take longer, cost more, and face greater challenges. If we're going to take humanity's first steps toward the stars, we should aim for the nearest target. The Breakthrough Starshot initiative, backed by visionaries including the late Stephen Hawking, billionaire Yuri Milner, and Facebook founder Mark Zuckerberg, proposed an audacious plan. They wanted to launch tiny spacecraft, each about the size of a postage stamp and weighing just a few grams, propelled by powerful Earth-based lasers. These miniature probes would be accelerated to 20% the speed of light through continuous laser pressure, pushing against ultra-thin reflective sails. At that velocity, the journey to Alpha Centauri would take approximately 20 years. Add another 4 years for the signals to return to Earth, and we're looking at a 24-year mission from launch to data reception. For the first time in human civilization, we possessed the theoretical knowledge and technological capability to send physical objects to another star system and receive data back within a single human lifetime. This represents a monumental shift in what's possible. Previous generations could only dream about reaching the stars. We can actually begin planning how to do it. The concept ignited imaginations globally. Funding poured in from private sources willing to invest in this grand vision. Top engineers from aerospace companies and research institutions developed miniaturized sensors that could fit on a microchip, tiny cameras capable of capturing images across light years, communication systems that could transmit data using milliwatts of power. Physicists calculated the precise laser array specifications needed to accelerate these postage stamp-sized spacecraft to relativistic velocities. They determined you'd need a laser array spanning several kilometers, generating gigawatts of power, all focused with extraordinary precision on a sail just meters across. The technical challenges are immense, certainly, but detailed engineering studies concluded that none appeared fundamentally impossible to overcome. We're not talking about science fiction technologies like warp drives or wormholes. We're discussing extensions of existing technology, difficult extensions requiring decades of development and billions in investment, but achievable within the bounds of known physics. The excitement reached fever pitch in 2016 when astronomers confirmed something extraordinary, a genuine game-changer in the search for habitable worlds. They announced the discovery of Proxima b, a planet orbiting Proxima Centauri, the smallest and closest member of the Alpha Centauri triple system. Proxima Centauri itself is what astronomers call a red dwarf star, measuring roughly 1/7 the diameter of our Sun. Imagine our Sun shrunk down to something not much larger than Jupiter. That's the scale we're talking about. It burns so dimly that despite being our nearest stellar neighbour, sitting closer to us than any other star in the entire galaxy, you cannot see it with your naked eye from Earth. You need at least a modest telescope to observe the closest star to our solar system. That's how dim red dwarfs really are. The planet, Proxima b, possesses approximately 1.3 times Earth's mass. It's not a gas giant like Jupiter or Saturn. It's a rocky world, what astronomers call a terrestrial planet, similar in composition to Earth, Venus, or Mars. Even more exciting, it orbits squarely within what astronomers call the habitable zone, sometimes called the Goldilocks zone. This is the region around a star where temperatures could theoretically permit liquid water to exist on a planetary surface. Not so close that water instantly boils away into steam, not so far that water freezes solid into ice. Just right for the chemistry of life as we understand it, for proteins to fold properly, for cellular biochemistry to function, for evolution to proceed. Headlines around the world erupted with variations of the same stunning announcement. Potentially, habitable world discovered right next door to Earth. Scientists confirm Earth-sized planet in habitable zone of nearest star. Could life exist just 4 light-years away? The media coverage was extensive and the public interest was enormous. People who normally paid no attention to astronomy suddenly wanted to know about Proxima b. Could there be aliens living on our cosmic doorstep? Could we visit them someday? Scientists immediately began speculating about conditions on this nearby planet. The questions came fast and furious. Could oceans cover portions of its surface? Liquid water oceans where chemistry could proceed and life might emerge? Might clouds drift through its atmosphere, water vapor condensing in an alien sky? Could life, even simple microbial life, have emerged in whatever waters might exist under alien skies? Could more complex organisms have evolved over billions of years? The possibilities seemed endless and thrilling. The discovery seemed almost cosmically convenient, almost too perfect to be coincidental. It was as if the universe had placed a potentially habitable world exactly where we needed it most, close enough that our most advanced telescopes could study it in unprecedented detail, close enough that interstellar missions, while still extraordinarily difficult, entered the realm of theoretical possibility rather than remaining pure fantasy. Some researchers wondered aloud whether this proximity might suggest something profound about how common habitable worlds are throughout the galaxy. Maybe every star has planets. Maybe habitable zones around most stars host terrestrial worlds. Maybe life is common and we just need to look for it. Additional observations revealed even more intriguing possibilities that fueled the growing excitement. Researchers found evidence suggesting a second planet, Proxima c, orbiting much farther out from the star. While this outer world appeared much less likely to host life due to extreme cold, its existence demonstrated something important. The Proxima Centauri system contained multiple planetary bodies. It wasn't just a star with one lucky planet. It was a planetary system, implying that planet formation had proceeded relatively normally around this red dwarf. Where there are two planets, there might be more waiting to be discovered. Meanwhile, studies of Alpha Centauri A and B, the larger binary pair orbiting each other at approximately 4.4 light-years away, hinted at possible planetary candidates around these sun-like stars as well. The data wasn't conclusive yet. Ground-based telescopes couldn't provide the precision needed for definitive confirmation, but the hints were tantalizing. Radial velocity measurements showed possible wobbles in the star's motions that might indicate orbiting planets, tugging them gravitationally. Transit observations suggested possible dips in starlight that might represent planets crossing in front of their stars from our perspective. The Alpha Centauri system began to look like it offered multiple opportunities for discovering worlds where conditions might support life as we know it. Not just one possible habitable planet, but potentially several across all three stars. The closest stellar system to Earth might be teeming with worlds, some perhaps harbouring life, others potentially suitable for future human colonization if we ever develop the capability to send people across interstellar distances. Teams of scientists started calculating in detail what conditions on Proxima b might actually be like in practice. The planet orbits extraordinarily close to its star, just 7.5 million kilometers away. To put that in perspective, Mercury, the closest planet to our Sun, orbits at about 58 million kilometers. Proxima b orbits roughly 8 times closer to its star than Mercury orbits the Sun. This extreme proximity results directly from Proxima Centauri's diminished energy output. Red dwarfs produce far less radiation than yellow stars like our Sun. Our Sun outputs about 400 trillion watts of energy. Proxima Centauri outputs only about 1/7 that amount. For planets to receive adequate warmth for liquid water, they must huddle much closer to their dim parent star. Some researchers grew cautiously optimistic that Proxima b might possess a thick atmosphere capable of distributing heat and maintaining stable temperatures across its surface. Earth's atmosphere plays this role beautifully. Heat from the sun-facing side gets distributed globally through atmospheric circulation, winds carrying warmth from equator to poles, preventing temperature extremes that would exist on an airless world. Perhaps Proxima b could do the same. Computer models explored various atmospheric scenarios, running thousands of simulations to test different possibilities. A dense carbon dioxide atmosphere, much thicker than Earth's current atmosphere, maybe more similar to Venus but not quite as extreme, might trap sufficient heat to warm the planet despite its relatively small size. Carbon dioxide is an excellent greenhouse gas, trapping infrared radiation and warming surfaces. Water vapor could create additional greenhouse effects similar to early Earth's atmosphere before oxygen became abundant. Some simulations suggested that Proxima b could maintain liquid water across significant portions of its surface under the right atmospheric conditions, if it had a thick enough atmosphere of the right composition. The planet might not resemble a tropical paradise with palm trees and sandy beaches. Conditions would be alien and potentially quite harsh by Earth standards, but it could conceivably support microbial life, simple organisms adapted to its unique environment. Maybe something like the extremophils we find in Earth's harshest environments, bacteria living in boiling hot springs or frozen Antarctic lakes, or deep underground in solid rock. Life doesn't require comfortable conditions, it just requires liquid water, energy sources, and the right chemical building blocks. Other scientists focused their attention on Proxima b's potential internal structure, what the planet might look like if you could slice it in half and examine its layers. A world containing 1.3 times Earth's mass might possess a larger iron core than our planet. Earth has an iron core about 7,000 kilometers in diameter. Proxima b's core might be larger, containing more iron and nickel. A larger core could potentially generate a stronger magnetic field through the dynamo process, where convection in the liquid metallic core generates electrical currents that produce magnetism. A stronger magnetic field would be beneficial because it could more effectively deflect harmful stellar radiation, creating a protective magnetosphere larger than Earth's. Active volcanism could release gases from the planet's interior that replenish whatever atmosphere might be lost to space over time. Earth's volcanoes continuously pump out water vapor, carbon dioxide, sulfur dioxide, and other gases. Without this replenishment, Earth's atmosphere would gradually be lost to space through various escape processes. If Proxima b has active geology, if its interior is hot enough to drive volcanism and tectonic activity, it could maintain an atmosphere over billions of years despite losses. Plate tectonics, the process where Earth's crust breaks into moving plates that collide and subduct and spread apart, might recycle surface materials back into the mantle and regulate planetary chemistry across geological timescales. Earth's plate tectonics is thought to be crucial for long-term climate stability, regulating carbon dioxide levels through weathering and subduction over hundreds of millions of years. If Proxima b has plate tectonics, it might maintain habitability through similar regulatory mechanisms. Perhaps Proxima b wouldn't merely survive in its challenging environment, but could actually thrive through geological processes that actively maintain habitability over billions of years, constantly adjusting and regulating to keep conditions suitable for life. The optimism was palpable in the scientific community during this period. Conference presentations about Proxima b drew packed audiences, standing room only at major astronomy meetings. Research papers about potential atmospheric compositions and surface conditions appeared in major journals like Nature and Science. Public interest surged as news outlets covered each new finding, each refinement of our understanding. Humanity seemed poised on the edge of a monumental discovery that would rank among the most important in history, right up there with the Copernican revolution or Darwin's theory of evolution. Our nearest stellar neighbour, sitting right next door in cosmic terms, might host a world where life could exist. The implications were almost too enormous to fully grasp. If the nearest star system hosts habitable planets, then the universe might be teeming with life. The search for extraterrestrial intelligence might not require us to look far at all. Contact with alien civilizations might be achievable within our lifetimes or our children's lifetimes. But then James Webb Space Telescope completed its deployment, calibrated its instruments with painstaking precision over months of careful testing, and turned its golden mirrors toward Alpha Centauri. What came back from those observations would transform optimism into something else entirely, something darker, something that forces us to completely reconsider our assumptions about where life can exist in this universe. To understand the magnitude of what James Webb discovered, you first need to appreciate what this telescope represents in the history of astronomy. Launched in December 2021 after literally decades of planning, construction, delays, budget overruns, and near cancellations, James Webb is not just another space telescope, not just a bigger version of Hubble. It's a revolutionary observatory that operates in ways fundamentally different from anything that came before it, seeing the universe in wavelengths invisible to human eyes and previous telescopes. The telescope's primary mirror spans 6.5 meters in diameter about 21 feet across, composed of 18 hexagonal segments that fit together like a golden honeycomb. Each segment is coated in ultra-thin gold, just a few atoms thick because gold reflects infrared light exceptionally well. The choice of gold wasn't aesthetic, it was driven by pure physics and the need to maximize infrared reflectivity. Infrared is where James Webb does its most groundbreaking work, observing heat signatures and thermal emissions that visible light telescopes like Hubble cannot see. This infrared sensitivity matters enormously when studying planets around other stars. Every object with a temperature above absolute zero, negative 273.15 degrees Celsius, emits thermal radiation. The hotter the object, the shorter the wavelength of its peak emission. The Sun, at 5800 degrees Kelvin, emits primarily invisible light. Planets in habitable zones around their stars, at temperatures ranging from maybe 200 to 400 degrees Kelvin, radiate most strongly in the mid-infrared spectrum, at wavelengths around 10 to 20 micrometers. This is precisely where James Webb's instruments achieve their maximum sensitivity. A planet at Earth-like temperatures glows faintly but detectably against the cold background of space which sits at just 3 degrees above absolute zero. James Webb can see that faint glow, can separate it from the overwhelming glare of the parent star, can analyze its spectrum to determine what molecules exist in the planet's atmosphere. It's an extraordinary capability that previous telescopes simply didn't have. Humanity seemed poised on the edge of a monumental discovery that would rank among the most important in history, right up there with the Copernican revolution or Darwin's theory of evolution. Our nearest stellar neighbour, sitting right next door in cosmic terms, might host a world where life could exist. The implications were almost too enormous to fully grasp. If the nearest star system hosts habitable planets, then the universe might be teeming with life. The search for extraterrestrial intelligence might not require us to look far at all. Contact with alien civilizations might be achievable within our lifetimes, or our children's lifetimes. But then James Webb Space Telescope completed its deployment, calibrated its instruments with painstaking precision over months of careful testing, and turned its golden mirrors toward Alpha Centauri. What came back from those observations would transform optimism into something else entirely, something darker, something that forces us to completely reconsider our assumptions about where life can exist in this universe. To understand the magnitude of what James Webb discovered, you first need to appreciate what this telescope represents in the history of astronomy. Launched in December 2021 after literally decades of planning, construction, delays, budget overruns, and near cancellations, James Webb is not just another space telescope, not just a bigger version of Hubble. It's a revolutionary observatory that operates in ways fundamentally different from anything that came before it, seeing the universe in wavelengths invisible to human eyes and previous telescopes. The telescope's primary mirror spans 6.5 meters in diameter, about 21 feet across, composed of 18 hexagonal segments that fit together like a golden honeycomb. Each segment is coated in ultra-thin gold, just a few atoms thick because gold reflects infrared light exceptionally well. The choice of gold wasn't aesthetic, it was driven by pure physics and the need to maximize infrared reflectivity. Infrared is where James Webb does its most groundbreaking work, observing heat signatures and thermal emissions that visible light telescopes like Hubble cannot see. This infrared sensitivity matters enormously when studying planets around other stars. Every object with a temperature above absolute zero, negative 273.15 degrees Celsius, emits thermal radiation. The hotter the object, the shorter the wavelength of its peak emission. The Sun, at 5800 degrees Kelvin, emits primarily invisible light. Planets in habitable zones around their stars, at temperatures ranging from maybe 200 to 400 degrees Kelvin, radiate most strongly in the mid-infrared spectrum, at wavelengths around 10 to 20 micrometers. This is precisely where James Webb's instruments achieve their maximum sensitivity. A planet at Earth-like temperatures glows faintly but detectably against the cold background of space which sits at just 3 degrees above absolute zero. James Webb can see that faint glow, can separate it from the overwhelming glare of the parent star, can analyze its spectrum to determine what molecules exist in the planet's atmosphere. It's an extraordinary capability that previous telescopes simply didn't have. The telescope orbits at the second Lagrange point, called L2, located about 1.5 million kilometers from Earth in the direction directly away from the Sun. This is a gravitationally stable location where the combined gravitational pull of Earth and Sun keeps the telescope in a stable orbit that moves in sync with Earth around the Sun. From this distant vantage point, James Webb maintains an unobstructed view of the cosmos, free from atmospheric interference that plagues even the best ground-based observatories, free from Earth's thermal glow and reflected sunlight that would contaminate sensitive infrared. Observations. The clarity and sensitivity are simply unmatched by any previous instrument humanity has ever constructed. We're talking about the ability to detect a bumblebee on the Moon. That's the telescope's angular resolution. We're talking about sensitivity that could detect the heat signature of a bumblebee at the distance of the Moon. These aren't just impressive numbers. They represent capabilities that open entirely new windows on the universe. James Webb's coronagraphs, specialized instruments designed specifically to block out the overwhelming light from stars, can suppress starlight by factors exceeding 10,000 to 1. Imagine trying to see a firefly hovering next to a searchlight from across the city. That's roughly the challenge of detecting planets next to their parent stars. The coronagraph creates an artificial eclipse, blocking the central star while allowing light from surrounding regions to reach the detectors. When turned toward Alpha Centauri, these coronagraphs could reveal planetary thermal signatures at angular separations corresponding to habitable zone distances, separations of just tens or hundreds of milliarc-seconds as seen from Earth. The telescope's spectrographs can analyze the chemical composition of planetary atmospheres by studying how starlight filters through them during transits. When a planet passes in front of its star from our perspective, an event called a transit, a tiny fraction of starlight passes through the planet's atmosphere before reaching us. This transmitted light carries information about what molecules exist in that atmosphere. Different molecules absorb light at characteristic wavelengths determined by their quantum mechanical energy levels, leaving unique fingerprints in the spectrum. Water vapor produces one distinctive pattern of absorption lines across the infrared spectrum. Carbon dioxide creates another completely different pattern. Oxygen has its own signature. Methane, ammonia, nitrogen, carbon monoxide, sulfur dioxide, and countless other compounds each leave their own spectral features that reveal their presence. James Webb can identify these molecular fingerprints with unprecedented precision, distinguishing between different possible atmospheric compositions, ruling out scenarios, confirming others. The telescope can measure temperature distributions across planetary surfaces by mapping how thermal emission varies with longitude and latitude. It can potentially detect biosignatures, chemical indicators that might suggest biological activity, combinations of gases like oxygen and methane that don't naturally coexist in atmospheres without continuous biological production. When astronomers announced they would point James Webb toward Alpha Centauri, expectations ran extraordinarily high throughout the scientific community and among space enthusiasts worldwide. The observation campaign would refine our understanding of this promising stellar neighborhood. The telescope would measure atmospheric compositions with accuracy impossible from ground-based facilities that must peer through Earth's turbulent atmosphere. Temperature distributions would be mapped across Proxima B's surface, revealing whether the planet maintains uniform temperatures or experiences extreme day-night variations. Chemical signatures that might indicate habitability or even biological activity would be searched for with instruments sensitive, enough to detect them if they existed at any substantial level. Proxima B had already captured public imagination as a potentially habitable world orbiting our nearest star. The media had run countless stories about this cosmic neighbour. Science fiction writers were already imagining stories set there. James Webb would transform speculation into hard data, replacing hope and imagination with concrete measurements and knowledge. The scientific community prepared for discoveries that would reshape humanity's understanding of where life might exist in the universe. The data, when it started arriving from the telescope's detectors, processed by computers, analysed by teams of astronomers working around the clock, did exactly that. It reshaped our understanding completely, but not in the way anyone had hoped or expected, not even in the way the most pessimistic scientists had feared. The reality was somehow worse than even the pessimists had predicted. The first shocking revelation from James Webb's observations concerned Proxima Centauri itself. the star hosting Proxima b, the star that had looked so promising from a distance, the star that hosted a planet in its habitable zone, turned out to be something far more violent and hostile than anyone had fully appreciated, despite years of ground-based observations. Proxima Centauri experiences stellar flares of extraordinary intensity, explosive magnetic eruptions that release enormous amounts of energy in very short time periods. These are not the modest flares our Sun occasionally produces during its 11-year activity cycle. During a major solar flare, the Sun's brightness might increase by a fraction of a percent for a few hours, releasing energy equivalent to millions of nuclear weapons but spread across its entire surface. It's dramatic, but not catastrophic for life on Earth. Our atmosphere and magnetic field protect us. But Proxima Centauri's flares are different beasts, entirely. We're talking about explosive eruptions that temporarily increase the star's brightness by factors exceeding 100, sometimes approaching or even exceeding 1,000 during the most extreme events. The star literally becomes 10 or even 100 times brighter than normal for hours or even days. During the most violent outbursts, Proxima Centauri emits ultraviolet and X-ray radiation at levels that would strip atmospheric molecules away from any planet orbiting in its habitable zone through a variety of destructive physical processes. Here's what makes this truly devastating for any hope of habitability. These flares don't occur occasionally, don't represent rare, unusual events that happen once every few years or decades. They happen constantly. James Webb's continuous monitoring capability, the ability to stare at a target for days or weeks without interruption, revealed that Proxima Centauri produces significant flare events, multiple times per week. Multiple times per week the star erupts with violence that would be catastrophic for nearby planets. Smaller eruptions, events that would still be considered major flares on the Sun, occur daily, sometimes multiple times per day. The star essentially exists in a permanent state of violent magnetic activity, churning and erupting continuously, releasing massive bursts of energy at frequencies far exceeding previous estimates that were based on ground-based observations. Ground telescopes had detected occasional flares from Proxima, yes, but they couldn't watch the star continuously, 24 hours a day for weeks on end. They caught glimpses, snapshots. James Webb provided continuous coverage that revealed the true extent of the violence. A planet orbiting this star doesn't experience occasional storms that life might hide from or adapt to. It faces permanent bombardment, continuous assault by radiation, and high-energy particles with no respite, no safe periods, no calm intervals when life could recover from damage. Consider the implications specifically for Proxima b given what we now know. The planet orbits just 7.5 million kilometers from its star, about 5% of the distance between Earth and our Sun. It receives the full force of these explosive events without any significant distance to diminish their intensity. When a major flare erupts from Proxima Centauri's surface, when the magnetic field lines snap and reconnect, releasing their stored energy, the radiation reaching Proxima b exceeds the star's normal output by factors exceeding 10,000 in certain critical wavelengths, particularly in the ultraviolet and X-ray regions of the spectrum that are most damaging to organic molecules and atmospheric gases. The planet's day side, the hemisphere permanently facing the star due to tidal locking, which we'll discuss more in a moment, would experience radiation levels during major flares that would sterilize exposed surfaces within minutes. Not hours, not days, but minutes of exposure during a major flare event would be sufficient to destroy any biological material we know of. Any hypothetical organisms caught without thick protective shielding would have their cellular chemistry destroyed almost instantaneously. DNA shredded by high-energy photons, proteins denatured by intense radiation, cell membranes disrupted by ionizing particles. We're not talking about gentle warming from a distant sun like Earth experiences. This is continuous bombardment by high-energy particles and ionizing radiation that would make even Venus, which experiences surface temperatures hot enough to melt lead, seem hospitable by comparison. Venus is hot, but it's a predictable, stable heat. Proxima b faces unpredictable spikes of lethal radiation on top of whatever baseline conditions exist. The radiation intensity during major flares exceeds lethal doses for most Earth organisms by factors of thousands. To put this in perspective, a dose of 5 to 10 sieverts of radiation is typically fatal for humans. causing acute radiation sickness and death within weeks. During a major Proxima Centauri flare, Proxima B's surface would receive doses measured in hundreds or even thousands of sieverts within minutes. Even extremophile organisms adapted to radiation-rich environments on Earth. Remarkable creatures like Deinococcus radiodurans that can survive radiation doses exceeding 5,000 times what would kill a human would struggle to survive the conditions that Proxima b endures routinely. But here's where it gets even worse. The flare activity represents only one aspect of the radiation environment, only one of multiple lethal mechanisms operating simultaneously. James Webb's spectroscopic analysis, detailed observations across multiple infrared wavelengths, searched methodically for the chemical signatures that should be present if Proxima b possessed an atmosphere of any significant density. This is not speculation or theoretical modelling. These are direct observations, actual measurements of light from the Proxima Centauri system, analysed with unprecedented precision. Atmospheres absorb and emit radiation at characteristic wavelengths determined by the quantum mechanical properties of their constituent molecules. These wavelengths act like fingerprints, unique identifiers revealing what gases are present. An Earth-like atmosphere would produce clear, unmistakable signatures of nitrogen, which makes up 78% of our atmosphere, oxygen at 21%, carbon dioxide, water vapour, argon, and trace amounts of other gases. Each of these would leave distinctive marks in the spectrum. Even a thick carbon dioxide atmosphere like Venus possesses, where carbon dioxide comprises over 96% of the atmospheric composition, would generate unmistakable spectral features, strong absorption bands at specific wavelengths that James Webb's instruments are specifically designed to detect. A methane atmosphere like Titan has would show its own distinctive signature. Any substantial atmosphere of any composition would produce detectable spectral features. The James Webb data, analysed by multiple independent teams to verify the results, showed essentially nothing. No nitrogen signature, no oxygen, no carbon dioxide absorption bands, no water vapour features, no methane, nothing consistent with an atmosphere of any significant density or composition. The spectral analysis suggested that Proxima b either never developed a substantial atmosphere in the first place during its formation, or it lost whatever atmosphere it once possessed to the relentless stellar radiation battering it continuously for billions of years since the planet formed. The planet likely presents a barren rocky surface directly exposed to the vacuum of space, continuously baked by unfiltered ultraviolet light at intensities that would instantly destroy organic molecules, and bombarded by stellar wind particles, charged protons and electrons travelling at hundreds of kilometers per second, impacting the surface with tremendous energy and causing continuous erosion and chemical alteration. Any water that might have existed on this world long ago when it was young, water delivered by comets and asteroids during the final stages of planetary formation, has evaporated and dissociated into its constituent elements. The hydrogen component, being the lightest element and therefore most susceptible to atmospheric escape, was stripped away into interstellar space over millions or billions of years. The oxygen either escaped as well or chemically bound with surface rocks, oxidizing iron and other metals in the crust and being permanently locked away in mineral form. The absence of atmospheric signatures carries profound implications that ripple through every aspect of potential habitability we might consider. Without an atmosphere, Proxima b cannot distribute heat from its day side to its night side. The planet almost certainly exists in what astronomers call tidal lock, a configuration where one hemisphere permanently faces the star while the opposite hemisphere remains in the eternal darkness, just as our moon always shows the same face to Earth due to tidal forces that have synchronized its rotation with its orbit. The day side continuously roasts under permanent stellar bombardment, while the night side freezes in perpetual cold, never receiving any direct starlight at all. Without atmospheric circulation to moderate these extremes, to carry heat from hot regions to cold regions, temperature differences between hemispheres could exceed 1000 degrees Celsius. The day side might be hot enough for rocks to glow red, or even partially melt during flare events. The night side might be cold enough for any remaining gases to freeze solid onto the surface. Without an atmosphere, liquid water cannot exist on the surface, regardless of average temperature or local conditions. This is fundamental physics, not negotiable. Liquid water requires atmospheric pressure to remain in liquid form. Below a certain pressure threshold, called the triple point, water can only exist as solid ice or water vapor gas. It cannot be liquid. In a vacuum or near vacuum, water either exists as ice if temperatures are cold enough, or it immediately vaporizes into space if exposed to any heat source. There's no pressure to hold it in liquid form. Without an atmosphere, ultraviolet radiation from Proxima Centauri reaches the ground completely unfiltered, unobstructed, at full intensity. Every damaging wavelength that would be absorbed by atmospheric gases on Earth hits Proxima B's surface directly. This radiation breaks apart any organic molecules that might form through random chemistry, dissociating them back into simpler components faster than any process could build them up into the complex structures life requires. Without an atmosphere, stellar wind particles impact the surface directly, rather than being deflected by upper atmospheric layers or absorbed in collisions with atmospheric molecules. Each impact kicks up atoms from the surface, a process called sputtering, very slowly eroding the surface and altering its chemistry over geological time. The cumulative effect over billions of years is substantial surface modification. The planet exists as bare rock exposed to the full fury of its parent star, and it's been like this for billions of years, for the entire history of the planetary system. The James Webb observations weren't catching Proxima b during a temporary bad phase, during an unusually violent period of stellar activity that might eventually calm down. This is the planet's permanent state, maintained by fundamental properties of the star it orbits, properties that won't change for trillions of years to come. To understand why Proxima Centauri behaves so violently, why it produces these continuous devastating flares, we need to examine how red dwarf stars differ fundamentally from our Sun in their internal structure and energy generation mechanisms. Stars like our Sun generate energy through nuclear fusion in their cores, where temperatures reach about 15 million degrees Celsius and pressures are enormous enough to force hydrogen nuclei to overcome their electrostatic repulsion and fuse into helium, releasing energy in the process. This energy then must work its way from the core to the surface, a journey that takes hundreds of thousands of years. In the Sun's interior, energy transport occurs primarily through radiative diffusion in what's called the radiative zone. Photons are absorbed and re-emitted countless times as they slowly work their way outward. Only in the outer 30% of the Sun's radius, in the convective zone, does energy transport occur through actual mass motion. Hot plasma rising and cool plasma sinking in enormous circulation patterns. Red dwarfs operate completely differently due to their much smaller mass. Their interiors remain fully convective throughout their entire volume from core to surface. Hot plasma rises directly from the fusion-producing core all the way to the visible surface, like water boiling vigorously in a pot where you can see bubbles rising from the bottom directly to the top. This convective activity transports energy efficiently, more efficiently than radiative diffusion, but it also generates powerful magnetic fields that become tangled and stressed over time through a complex process not fully understood but extensively modelled. The churning convective motion twists magnetic field lines into increasingly complex configurations, wrapping them around each other, stressing them like rubber bands twisted tighter and tighter. These stressed field lines store enormous amounts of magnetic energy that accumulates over days or weeks as the convection continues churning. When the magnetic field configuration becomes too stressed, when it can't maintain its current topology any longer, the field lines suddenly snap and reconnect into a simpler, lower energy configuration. This magnetic reconnection process releases the stored energy explosively in the form of a stellar flare, accelerating particles to tremendous velocities, heating plasma to tens of millions of degrees, and producing intense bursts of radiation across the electromagnetic spectrum from radio waves to X-rays. It's similar to what happens on the Sun during solar flares, yes, but the scale is completely different because of the fully convective structure of red dwarfs. A major solar flare might increase the Sun's brightness by a fraction of a percent for a few hours, releasing energy equivalent to tens of millions of nuclear weapons, but spread across the Sun's enormous surface area and over several hours. It's dramatic but relatively modest compared to the Sun's total energy output. A major Proxima Centauri flare increases that star's brightness by factors of hundreds, or sometimes thousands. releasing energy equivalent to millions of thermonuclear weapons detonating simultaneously, focused on a star much smaller than the Sun, so the intensity per unit area becomes even more extreme. For a planet orbiting close enough to receive habitable temperatures during normal stellar conditions, these flare events are absolutely catastrophic. The relative impact on orbiting planets depends not just on the absolute energy released, but also on orbital distance. Earth orbits 150 million kilometers from the Sun, enjoying a comfortable distance that provides warmth without overwhelming radiation. Proxima b orbits just 7.5 million kilometers from its star, 20 times closer in linear distance. Since radiation intensity follows an inverse square law, spreading out and weakening with the square of the distance from the source, this means that at Proxima b's orbital distance, the same amount of stellar output produces 400 times more intense radiation than at Earth's orbital distance. 400 times more intense. Let that sink in for a moment. When a flare increases Proxima Centauri's output by a factor of 100, Proxima b receives 40,000 times more radiation than Earth would receive during a comparable solar event. 40,000 times. The numbers become almost incomprehensible. We're talking about radiation environments so extreme that they challenge our ability to find appropriate analogies from human experience. Red dwarfs also remain magnetically active far longer than Sun-like stars, essentially forever by human standards. Our Sun will exhaust its hydrogen fuel in roughly 5 billion years as it gradually fuses hydrogen into helium in its core. Once the core hydrogen is depleted, the Sun will expand dramatically into a red giant, engulfing Mercury and Venus and possibly Earth, burning helium in its core for a while before eventually shedding its outer layers as a planetary nebula and fading to a white dwarf, a dense cooling ember about the size of Earth. Proxima Centauri burns its hydrogen fuel so slowly, at such a measured pace due to its low core temperature and pressure, that it will continue shining for trillions of years, hundreds of times longer than our Sun's entire lifespan from birth to death. The universe itself is only about 14 billion years old. Proxima Centauri will still be shining when the universe is 1,000 times older than it is now. This might seem beneficial for life at first consideration. More time means more opportunity for biological evolution to operate, more chances for complex life to emerge, more stability for civilizations to develop. But the reality is exactly the opposite. The extended active phase means planets orbiting red dwarfs face continuous radiation bombardment for billions or even trillions of years longer than planets around Sun-like stars. The magnetic activity that drives flares doesn't diminish over time. It continues essentially indefinitely as long as the star remains fully convective. James Webb observations confirmed something that theoretical models had predicted, but that astronomers needed to verify with actual measurements. Proxima Centauri's flare activity shows no signs of diminishing, despite the star being roughly 4.8 billion years old, similar in age to our Sun. The magnetic dynamo driving these explosive outbursts operates with sustained intensity throughout a red dwarf's lifetime. It doesn't calm down with age like Sun-like stars do. It maintains maximum violence from youth through old age spanning trillions of years. Planets in the habitable zones of such stars don't face temporary violence that might eventually improve. They face eternal siege, continuous assault with no end ever, no reprieve, no calm future awaiting. The conditions Proxima b experiences today are the conditions it has experienced for billions of years and will continue experiencing for billions or trillions more years into the future. The implications extend beyond simple atmospheric loss, beyond the obvious problem of having your atmosphere blown away into space, to the fundamental chemistry required for habitability and life's emergence. Life as we understand it, all life on Earth from the simplest bacteria to the most complex organisms, requires certain complex organic molecules to form and persist over geological timescales. These molecules include amino acids, the building blocks that link together to form proteins. They include nucleotides, the components of DNA and RNA that store and transmit genetic information. They include lipids, fatty molecules that form cell membranes and compartmentalize cellular chemistry. They include countless other compounds necessary for cellular structures and biochemical processes. Ultraviolet radiation efficiently destroys these molecules by breaking chemical bonds and inducing harmful reactions. A ultraviolet photon carries enough energy to snap carbon-carbon bonds, to break apart aromatic rings, to dissociate complex molecules back into simpler components. Complex organic chemistry simply cannot proceed, cannot build up the molecular inventory life requires, when the building blocks are continuously demolished by incoming radiation faster than any chemical process can synthesize new ones. On Earth, our atmosphere filters most incoming ultraviolet radiation before it reaches the surface where life exists. The ozone layer in our stratosphere at altitudes between 15 and 35 kilometers absorbs the particularly damaging wavelengths between 200 and 300 nanometers that would otherwise sterilize exposed environments. This ozone shield protects life on land and in shallow waters from radiation that would destroy cellular chemistry. The ozone itself forms through a natural photochemical process. Ultraviolet light breaks apart oxygen molecules in the upper atmosphere, creating individual oxygen atoms. These free oxygen atoms then combine with intact oxygen molecules to form ozone, a 3-oxygen molecule. The ozone then absorbs incoming ultraviolet, breaking back down into oxygen. This continuous cycle maintains the ozone layer as long as oxygen remains abundant in the atmosphere. It's self-sustaining and self-repairing. Early Earth lacked this ozone layer because oxygen was not yet abundant in the atmosphere. The primordial atmosphere contained nitrogen, carbon, dioxide, water vapor, maybe some methane and ammonia, but very little free oxygen. Oxygen is actually quite reactive and doesn't persist in atmospheres without continuous replenishment. On Earth, that replenishment comes from photosynthesis, from plants and algae, and cyanobacteria splitting water molecules and releasing oxygen as a waste product. Life originated on early Earth in ocean depths, where hundreds of meters of water provided protection, equivalent to our modern atmospheric shield. Water absorbs ultraviolet radiation very effectively. By the time ultraviolet light has penetrated even a few meters into the ocean, its intensity has diminished by orders of magnitude. By the time you're at 10 or 20 or 50 meters depth, you're protected from surface ultraviolet as effectively as you would be under a thick atmosphere. Early life remained in these protected depths for billions of years. Only after photosynthetic organisms had spent billions of years producing oxygen, gradually accumulating it in the atmosphere through the steady waste production of countless generations, did oxygen become abundant enough for ozone formation to occur. Once the ozone layer formed, probably sometime between 2 and 2.5 billion years ago, during what's called the Great Oxidation Event, life could finally colonize land surfaces that had previously been too dangerous for complex biology. This transition from ocean-bound life to land-dwelling life required billions of years of biological evolution and atmospheric modification. Proxima b cannot replicate this protective pathway through any mechanism we can identify. The planet lacks the atmosphere necessary for ozone formation or any other radiation-absorbing process. It lacks the surface liquid water to provide a protected environment where early life might originate and persist while gradually modifying atmospheric conditions. It lacks the geological activity to produce volcanic gases and maintain atmospheric pressure against escape processes. Without an atmosphere to absorb ultraviolet radiation, Proxima b's surface receives the full intensity of its star's violent output. During normal stellar conditions between flares, ultraviolet intensity would already be damaging to organic chemistry. During flare events, ultraviolet radiation spikes to levels that would destroy any exposed organic molecules within minutes or even seconds. Any amino acids, any nucleotides, any complex organic compounds are instantly dissociated back into simpler molecules or even individual atoms. Without surface water to act as a radiation shield, there exists no protected environment where chemistry could proceed uninterrupted. On Earth, even when the surface was being sterilized by ultraviolet, life persisted in deep ocean waters where it remained protected. Proxima b has no oceans, no deep lakes, no protected aquatic environments, where chemistry could proceed sheltered from the radiation onslaught. Without geological activity, without active volcanism and tectonic processes constantly releasing gases from the planetary interior, there exists no mechanism to replace atmospheric molecules that are stripped away by stellar radiation, or to maintain atmospheric pressure against the various escape processes operating continuously. Earth's volcanoes continuously replenish atmospheric losses. Proxima b lacks this replenishment mechanism. Every pathway that allowed life to emerge and persist on Earth over billions of years is completely blocked on Proxima b. Every single one. There's no workaround, no alternative pathway, no clever adaptation that could overcome these fundamental obstacles. And here's the truly devastating realization. The fundamental problem doesn't lie with Proxima b itself, doesn't result from any particular properties of the planet that might be different on another world. The problem lies with the star it orbits. No planetary characteristics can compensate for a stellar environment that continuously destroys the prerequisites for habitability. Imagine a hypothetical planet with every advantage we can conceive. Give it a thick atmosphere, 10 times thicker than Earth's. Give it a magnetic field twice as strong as Earth's. Give it deep oceans covering most of its surface. Give it active plate tectonics and vigorous volcanism constantly replenishing atmospheric losses. Pack it with every favourable characteristic we can think of. Now place this ideal planet in orbit around Proxima Centauri at the distance required for habitable temperatures. That thick atmosphere would be stripped away by stellar winds and flare radiation faster than volcanism could replenish it. The strong magnetic field would be overwhelmed by particle bombardment, exceeding anything Earth experiences by orders of magnitude. Those deep oceans would be vaporized and their water molecules photodissociated by ultraviolet light, the hydrogen stripped into space and the oxygen bound into surface rocks. Life in those oceans would be irradiated into extinction during routine stellar flare activity. The violence inherent to Proxima Centauri's fundamental nature, resulting from its fully convective interior and the powerful magnetic dynamo that produces, dooms any world orbiting close enough to receive the warmth necessary for liquid water temperatures. You cannot have habitable temperatures without also receiving lethal radiation doses. The two are inseparably linked by the physics of stellar radiation and the distance required for adequate warmth from a dim star. The Alpha Centauri observations and the detailed analysis of Proxima b specifically provide overwhelming evidence for something that scientists had long suspected based on theoretical modelling, but couldn't definitively prove without actual measurements. Red dwarf habitable zones might be fundamentally unsuitable for life, despite being labelled as habitable based purely on temperature considerations. Temperature alone does not determine habitability. Radiation environment matters just as much, or more. And here's where this becomes truly disturbing for the broader search for life in the universe. Red dwarf stars like Proxima Centauri aren't rare cosmic oddities or unusual examples. They're the most common type of star in the galaxy by an enormous margin. Approximately 70% of all stars in the Milky Way are red dwarfs. 70%. If you could somehow select a star at random from our galaxy's 400 billion stars, the odds are 7-3 that you'd draw a red dwarf rather than any other stellar type. Their extreme longevity, burning for trillions of years compared to the mere billions our Sun will last, provides vastly more time for life to potentially emerge and evolve on any planets they host. An organism on a red dwarf planet would have 1 trillion years to evolve intelligence, instead of the mere 4 billion years that life on Earth has had so far. The timescales are so different that they seem to favour red dwarfs for hosting advanced life despite any challenges the stellar environment might present. This combination of overwhelming abundance and extreme longevity made red dwarfs attractive targets in the search for extraterrestrial life. Some researchers argued enthusiastically that red dwarf planets should dominate any cosmic census of inhabited worlds, simply because red dwarfs dominate the stellar population so thoroughly. If habitable worlds exist around red dwarfs at rates even modestly lower than around Sun-like stars, the sheer number of red dwarfs would still produce more total habitable worlds just through overwhelming numbers. The galaxy might be filled with life clustered around dim red stellar furnaces rather than bright yellow stars like our Sun. We might be the unusual ones, orbiting a star that's actually in the minority, while most life exists in red dwarf systems adapted to those particular conditions in ways we can barely imagine. What do you think about these discoveries? Does knowing that our nearest neighbour is uninhabitable change how you view Earth's uniqueness? The evidence is forcing scientists to completely reconsider where life can exist, and whether we might truly be alone in ways we never imagined possible. James Webb's observations of Proxima Centauri devastate this optimistic view, completely and comprehensively. The same stellar characteristics that produce red, Dwarf longevity, that allow them to burn steadily for trillions of years, also generate sustained violent activity that systematically destroys planetary habitability through multiple redundant mechanisms. The fully convective interiors that we discussed earlier create powerful magnetic fields that drive continuous flare activity throughout these stars' lifetimes, with no diminishment, no calm period, no improvement with age. The magnetic dynamos operating in red dwarf interiors show no signs of weakening as the stars mature. Old red dwarfs, stars that have been burning for billions of years, remain just as violently active as young red dwarfs that formed only recently on cosmic timescales. The flare activity isn't a characteristic of stellar youth that calms down over time. It's a fundamental feature of the stellar type that persists essentially forever. Their compact habitable zones, resulting from their dim energy output, require planets to orbit close enough for rapid tidal locking to occur and for maximum stellar wind exposure. Remember that radiation intensity follows an inverse square law. To receive Earth-like warmth from a star that outputs only 1/7 the Sun's energy, you need to orbit about 20 times closer. But this 20-fold decrease in orbital radius produces a 400-fold increase in radiation intensity for any given stellar output. The warmth needed for liquid water comes packaged unavoidably with radiation levels that strip atmospheres and sterilize surfaces. You cannot separate the two factors. You cannot dial down the radiation while keeping the warmth. They're linked by fundamental physics. The habitable zone around red dwarfs, where temperatures permit liquid water, is simultaneously a kill zone where radiation destroys atmospheres and sterilizes surfaces, and this appears to be a fundamental characteristic of red dwarf systems, rather than an unfortunate exception that applies only to Proxima Centauri specifically. Now, you might wonder whether Proxima Centauri represents typical behaviour for its stellar class, or whether it might be an anomalous outlier that happens to be particularly violent. Maybe Proxima is just an unusually active red dwarf, and most red dwarfs behave more calmly, producing less frequent or less intense flares that wouldn't be as devastating to planetary habitability. This is a crucial question because the implications for the galaxy depend heavily on whether Proxima's behaviour generalises. James Webb has observed dozens of other red dwarfs throughout its operational lifetime since achieving full operational capability. The telescope has examined red dwarfs at various distances from Earth, red dwarfs of different ages, red dwarfs with different masses ranging from the smallest stars, barely massive enough to sustain fusion, up to the largest red dwarfs approaching the mass threshold, where stars transition to being orange K-type stars rather than red M-type dwarfs. The sample spans the range of red dwarf properties and circumstances, providing a statistical view of how these stars behave across their population. The results are remarkably consistent and deeply troubling. The observations find similar activity levels across the sample population. Violent flare behaviour isn't exceptional for red dwarfs. It's not something only a few particularly active examples exhibit. It's characteristic of the entire stellar class. Red dwarfs examined by James Webb show flare rates, stellar wind densities, and ultraviolet emission levels that cluster around values comparable to Proxima Centauri, rather than being distributed across a wide range that might include calm, quiet examples suitable for hosting habitable planets. Some red dwarfs are somewhat more active than Proxima. Some are somewhat less active. But the differences are modest, factors of 2 or 3, rather than factors of hundreds or thousands. No examined red dwarfs show activity levels low enough that planets in their habitable zones could maintain substantial atmospheres over billions of years. None display the calm, stable output that would permit complex organic chemistry to proceed uninterrupted on planetary surfaces. The nearest red dwarf to Earth turns out to be typical of its kind, representative rather than exceptional. The violence we see at Proxima Centauri characterizes red dwarfs throughout the galaxy. This finding effectively eliminates roughly 70% of all stars in the galaxy from consideration as potential hosts for habitable worlds. The most numerous stellar type in the galaxy, the stars that make up the majority of the stellar population, almost certainly cannot support life as we understand it anywhere in their habitable zones. Whatever life exists elsewhere in the universe must arise around the minority of stars that behave more calmly than red dwarfs, around sun-like stars or possibly orange K-type stars that might offer intermediate conditions. When you eliminate 70% of the galactic stellar population from habitability consideration, the pool of candidates for life-bearing worlds shrinks dramatically. Previous calculations about how many habitable planets might exist in the galaxy often heavily weighted red dwarf planets in their estimates due to red dwarf abundance. Calculate the number of planets per star, multiply by the number of stars, weight heavily toward red dwarfs, since they're 70% of the population, and you get enormous numbers of potentially habitable worlds. If we must now exclude essentially all red dwarf planets from habitability consideration based on measured stellar violence rather than optimistic assumptions, those billions of potential habitable worlds shrink to perhaps hundreds of millions or even just millions. The correction factor is enormous, perhaps reducing estimates by 1 or even 2 orders of magnitude. But the news gets worse when we examine Alpha Centauri A and B, the sun-like stars that we hoped might offer better prospects than their violent red dwarf companion. Surely these calm, stable, sun-like stars would host habitable planets, right? They don't produce the violent flares characteristic of red dwarfs. Their habitable zones lie at comfortable distances similar to Earth's orbit around our Sun. Planets there wouldn't be tidally locked. They could rotate normally, have day-night cycles, maintain atmospheric circulation. Everything should work out fine around these stars. The James Webb observations tell a very different story, one equally disturbing but for completely different reasons, having nothing to do with stellar violence. Alpha Centauri A shines with the warm yellow light of a G-type star, nearly identical to our Sun in most measurable properties. Its surface temperature reaches approximately 5800 Kelvin, the same as our Sun within measurement uncertainties. It produces that familiar golden glow we see every day. With roughly 10% more mass than the Sun and about 23% greater diameter, Alpha Centauri A represents what our own star might look like if it had formed with slightly more raw material from its natal molecular cloud. It's not identical to the Sun, but it's remarkably similar, as close a twin as we're likely to find among nearby stars. Spectroscopic analysis reveals chemical composition remarkably similar to the Sun's, with similar abundances of hydrogen, helium, carbon, nitrogen, oxygen, and heavier elements. This suggests both stars, formed from comparable interstellar material in their respective stellar nurseries, clouds with similar chemical enrichment histories. Its companion, Alpha Centauri B, glows with the cooler orange hue characteristic of K-type stars. Stars slightly smaller and cooler than the Sun, but still quite capable of supporting habitable zones. This smaller stellar furnace contains approximately 90% of the Sun's mass and produces about half the luminosity, half the total energy output. Surface temperatures hover around 5300 Kelvin, warm enough to sustain nuclear fusion in the core but noticeably cooler than either the Sun or Alpha Centauri A, which explains the orange rather than yellow colour. Despite its reduced output compared to the Sun, Alpha Centauri B still possesses sufficient energy to warm planets across a meaningful, habitable zone extending from perhaps half an astronomical unit to 1.5 astronomical units from the star. That zone would lie closer to the star than Earth's orbit around the Sun, since the star is dimmer, but it's still a respectable distance that would avoid tidal locking and allow normal planetary rotation. From Earth, separated by over 4 light-years of empty space, these two stars appear as a single bright point of light in the southern sky, one of the brightest objects visible from southern hemisphere locations. Only through telescopic observation can we resolve them as separate objects rather than a single star. They orbit each other at distances ranging from 11 astronomical units at closest approach to 36 astronomical units at their most distant separation. That orbital range is comparable to the span between Saturn at roughly 9 to 10 astronomical units and Pluto, which orbits at about 39 astronomical units in our solar system. Their orbital period, the time required to complete one orbit around their common centre of mass, lasts approximately 79 years. That's longer than a typical human lifespan. The stars complete less than one full orbit during a human lifetime. A person born when the stars were at their closest approach to each other would reach middle age, perhaps 50 or 60 years old, before the stars separated to their maximum distance. Then they'd need to live to be over 100 years old to see the stars complete the orbit and return to close approach again. At first glance, considering just the stars themselves without thinking about gravitational dynamics, a planet circling either star at the appropriate distance might enjoy conditions superficially similar to Earth. The stellar radiation would be stable and predictable. Unlike the violent Proxima Centauri with its constant flare activity, these larger stars possess the layered internal structure with distinct radiative and convective zones that produces relatively calm stellar surfaces. They don't undergo the dramatic flare events that make red dwarfs so hostile to planetary habitability. They experience stellar activity cycles similar to our Sun's 11-year sunspot cycle, magnetic activity cycles with periods of higher and lower surface activity that produce modest variations in output over time. During solar maximum, the Sun produces more sunspots, more small flares, slightly higher ultraviolet output. During solar minimum, activity decreases and the Sun becomes quieter. Alpha Centauri A and B undergo similar cycles, producing variations in their output of perhaps a few tenths of a percent rather than the factors of hundreds variations that characterize red dwarf flares. This should create stable, predictable conditions suitable for life. Organisms could evolve in an environment where stellar radiation varies only modestly and predictably over time. Atmospheres could persist without being stripped away. Liquid water could exist on surfaces without being vaporized by flare activity. Every indication suggests these sun-like stars should be excellent hosts for habitable planets. But this optimistic assessment collapses completely when you examine the gravitational dynamics of the system, when you consider how these two stars affect each other and anything orbiting around them. Alpha Centauri A and B don't merely coexist peacefully at comfortable distances, each going about its business without affecting the other. They engage in an elaborate gravitational dance that profoundly affects any planetary systems attempting to form around either star or attempting to maintain stable orbits over billions of years. Their elliptical orbit brings them as close as 11 astronomical units every 79 years. Close enough that gravitational interactions become significant, close enough to gravitationally perturb objects throughout both stellar vicinities. This periodic disruption that occurs every 8 decades creates conditions fundamentally hostile to the stable planetary orbits that life requires over billions of years. Life on Earth required about 4 billion years to evolve from simple single-celled organisms to complex intelligent beings. Any habitable planet needs to maintain stable conditions for comparable timescales to have any reasonable chance of developing complex life or intelligence. But orbital instabilities operating on timescales of millions of years or even just hundreds of thousands of years would prevent this long-term stability. James Webb's extended observation campaigns search systematically for thermal signatures and reflected light from any planets orbiting Alpha Centauri A or B. The telescope's infrared sensitivity and angular resolution should easily reveal Earth-sized worlds at distances corresponding to habitable zones around these sun-like stars. If planets exist there, if they're massive enough and warm enough to produce detectable thermal emission, James Webb should see them. Earlier ground-based observations from facilities like the European Southern Observatory's Very Large Telescope in Chile had suggested possible planetary candidates based on radial velocity measurements, showing subtle wobbles in the star's motions that might indicate gravitational tugs from orbiting planets. But those ground-based hints required confirmation with more sensitive space-based instruments that could observe continuously without atmospheric interference. What James Webb found wasn't planets. The search yielded no confirmed detections of planetary thermal signatures in the habitable zones of either star despite observation campaigns spanning many months and using multiple detection techniques. Instead of planets, the telescope found evidence of catastrophically disrupted circumstellar material around both stars, debris where planets should have formed but apparently didn't or couldn't. This discovery requires understanding how planetary systems form in the first place. When stars form from collapsing molecular clouds, when gravity pulls diffuse gas and dust together into increasingly dense clumps that eventually become hot enough in their centers to ignite fusion, the process inevitably produces rotating disks of leftover material surrounding the young stars. These protoplanetary disks contain all the raw ingredients for building worlds. Silicate dust particles, grains of rocky material like tiny bits of sand, will gradually stick together through gentle collisions to form larger pebbles, then boulders, then kilometer-sized planetesimals, eventually accumulating into rocky cores massive enough that their own gravity dominates and allows rapid runaway growth into true planets. Ice particles farther from the star, where temperatures drop below freezing for water, carbon dioxide, ammonia and methane will similarly accumulate and contribute to planet formation, delivering volatiles that become atmospheres and oceans. Gas in the disk can be gravitationally captured by sufficiently massive cores, forming giant planets like Jupiter and Saturn. The entire process proceeds systematically over millions of years in a maturing disk. The orderly architecture of our solar system, with its inner rocky planets, middle asteroid belt, outer gas giants, and distant icy objects, reflects the systematic processes that occurred in the disk surrounding our young sun 4.6 billion years ago. Observations of young stars throughout our galaxy show that protoplanetary disks are nearly universal. Essentially every forming star produces a disk, and essentially every mature star that we examine closely shows evidence of having hosted a disk when it was young. Alpha Centauri A and B show spectral signatures and infrared observations indicating their protoplanetary disks suffered catastrophic disruption early in the system's history. The gravitational interaction between the two stars during their closest approaches every 79 years would have stirred and scattered disk material rather than allowing it to settle into stable orbits, where systematic planet formation could proceed normally over millions of years. Computer simulations of binary star formation, detailed numerical models that track millions of individual particles through thousands of orbital periods, demonstrate conclusively that tight binary pairs like Alpha Centauri A and B regularly destroy or severely truncate the planet-forming disks around their component stars. The physics follows inevitably from gravitational dynamics, from Newton's law of gravitation, and Kepler's laws of orbital motion, applied to systems with two massive bodies rather than one. When two stars approach within tens of astronomical units, not just once but repeatedly every few decades, their combined gravitational field creates tidal forces that stretch and distort any disk material orbiting either star. Think of how the Moon creates tidal forces on Earth, pulling ocean water into bulges that follow the Moon's orbital motion. Now imagine forces vastly stronger affecting solid, particles and gas in a protoplanetary disk. Particles that were peacefully following nearly circular orbits around one star, drifting along at predictable velocities determined by their distance from the star, suddenly feel strong gravitational pulls from the companion star during its closest approach. The force from the companion star pulls them slightly away from their original orbits. Their orbital paths become elongated, stretched into ellipses rather than remaining circular. Some particles get pulled onto trajectories that carry them closer to their star, others get pushed onto paths that carry them farther out. These disrupted orbits begin crossing each other's paths, rather than remaining in separate non-intersecting circles like cars on different lanes of a racetrack. Particles that were maintaining safe distances suddenly find themselves on collision courses. When orbits cross, collisions become inevitable over time. Particles moving at different speeds on intersecting paths must eventually hit each other. The first collisions occur at modest velocities, perhaps a few meters per second, speeds comparable to a person walking briskly. At these gentle speeds, some collisions result in particles sticking together through electrostatic forces or material cohesion, beginning to build larger aggregates through a process called accretion. This is the constructive phase of planet formation, where small objects gradually merge into larger ones. But the gravitational perturbations don't stop after one binary orbit. They continue with each pass of the binary companion, repeating every 79 years, continuously stirring the disk and increasing orbital eccentricities further. With each binary orbit, gravitational tugs accumulate their effects on disk particles. Orbital eccentricities grow higher with each stellar pass. Orbital inclinations tilt progressively out of the original disk plane as particles get tugged up and down as well as in and out. Particles that survived the first wave of collisions and perhaps even grew slightly through accretion now face crossing velocities of tens of meters per second during their next collisions, speeds comparable to vehicles on city streets. At these elevated speeds, the nature of collisions changes fundamentally. Instead of gently merging, particles begin to fragment upon impact. Silicate grains shatter when struck hard enough. The larger aggregates that had begun forming through gentle accretion are pulverized back into their constituent particles when hit at higher speeds. The constructive phase of planet building, the accumulation of small particles into larger bodies, reverses into destructive grinding where collisions break things apart rather than building them up. And there's no way to stop this reversal, because the binary companion keeps returning every 79 years, continuing to stir the disk and maintain high orbital eccentricities and collision velocities. The violence escalates even further as the most highly perturbed particles achieve crossing velocities of hundreds of meters per second, speeds comparable to commercial aircraft. Impacts at these extreme speeds don't just fragment the colliding particles, they literally vaporize portions of the colliding bodies, converting solid material into expanding clouds of gas and microscopic debris. The kinetic energy of impact gets converted into heat. Temperatures spike to thousands of degrees at the collision point. Solid rock flash vaporizes into plasma. The energy released in these hypervelocity collisions heats the surrounding disk material, driving off volatile compounds that might otherwise have contributed to planetary atmospheres or oceans. Water ice sublimates directly from solid to vapor without passing through liquid phase. Methane and ammonia ice also vaporize. These volatile gases then get blown away by stellar radiation pressure or stellar winds, lost from the inner disk region entirely. What remains becomes depleted in volatiles, baked dry. The disk transforms from a nurturing nursery of forming worlds into a demolition zone, where nothing substantial can survive or accumulate. Construction gives way to destruction. Growth reverses to grinding. The raw materials for planets get progressively shattered into smaller pieces rather than accumulating into larger bodies. Over millions of years of this continuous grinding, the disk mass itself diminishes as material gets either ground fine enough to be blown away by stellar radiation pressure or perturbed onto trajectories that cause it to fall into one of the stars, or be ejected from the system entirely into interstellar space. The separation distance between Alpha Centauri A and B, ranging from 11 to 36 astronomical units, falls into a particularly problematic range for planet formation that planetary scientists have identified through theoretical studies and numerical simulations. This range is sometimes called the disruption zone, the configuration that maximizes interference with planet formation while still allowing the stars to orbit relatively close together. Stars separated by only a few astronomical units, pairs orbiting so close they nearly touch, can maintain stable circumstellar disks that extend modestly outward from each star before reaching the gravitational boundary where the companion star's influence dominates. These extremely tight binaries function almost like single stars gravitationally, and planets can form in circumbinary orbits around the pair as if they were a single gravitational entity. Stars separated by hundreds of astronomical units, pairs orbiting so far apart they barely influence each other gravitationally, barely interact with each other's planetary systems at all. Each star maintains its own independent protoplanetary disk that evolves essentially as if the companion didn't exist. Planets form normally around each star with minimal interference from the distant companion. The companion is simply too far away for its gravitational perturbations to significantly affect disk dynamics or planetary orbits. But the intermediate separation range exemplified by Alpha Centauri A and B creates the worst possible conditions. The stars are close enough that their gravitational perturbations significantly affect disk material and planetary orbits around each component. But they're too far apart to function as a single gravitational entity that planets could orbit in circumbinary configuration. They're in the middle ground where maximum disruption occurs. Numerical simulations conducted by research teams worldwide, simulations run on supercomputers tracking millions of virtual particles through billions of years of virtual time, have explored planet formation in Alpha Centauri-type binary systems extensively. These simulations include all the relevant physics, gravitational interactions, collisions, tidal forces, radiation pressure, gas drag, everything that affects disk particles and planet formation. The results are remarkably consistent across different research groups, using different numerical codes and different initial conditions. They consistently show that disk material in the regions corresponding to habitable zones around either star experiences particularly intense disruption. The zones where temperatures would be suitable for liquid water receive the worst of the gravitational chaos. Material closer to either star well inside the habitable zone, where temperatures would be too hot for liquid water, might survive the gravitational stirring because particles there orbit faster and have shorter orbital periods that help them avoid the worst resonances with the binary orbit. Material far from both stars, well outside the habitable zones where temperatures would be too cold, also remains relatively undisturbed because the binary perturbations weaken with distance. But the habitable zones themselves, the regions we care most about for potential life, sit right in the sweet spot of maximum disruption. The gravitational stirring is strong enough there to prevent stable planet formation, but not strong enough to simply eject all material immediately. Instead, material gets ground down over millions of years in this zone of maximum chaos. No simulation across dozens or hundreds of runs by different research teams has successfully produced Earth-sized planets in stable habitable zone orbits around either Alpha Centauri A or Alpha Centauri B. The gravitational stirring from the binary companion prevents it. Orbital eccentricities grow too large. Collision velocities exceed the threshold for constructive accumulation. Planet formation never progresses past the early stages of planetesimal formation before being reset by the next binary perturbation. Some simulations produce planets in very close orbits, circling either star at distances well inside the habitable zone, where temperatures would be far too hot. Other simulations produce planets in very distant orbits, circling far outside the habitable zones in cold regions. But nothing forms and survives in the habitable zones themselves, and those are the only orbits we care about for potential life. James Webb detected faint infrared excess around both Alpha Centauri A and B, excess emission beyond what the stellar photospheres themselves produce. This infrared excess is consistent with sparse debris disks, collections of dust and small particles produced by collisions between remnant larger bodies like asteroids. These debris disks are the leftover wreckage from failed planet formation, material that couldn't accumulate into planets, grinding itself down through mutual collisions. Unlike the rich, massive protoplanetary disks that surrounded our Sun 4.6 billion years ago, disks containing enough material to build multiple terrestrial planets and several gas giants, the debris disks around Alpha Centauri A and B contain only scattered remnants. The total mass of detectable debris amounts to less than 1% of the material that built the terrestrial planets in our solar system. Less than 1%. The vast majority of the original disk material has been lost, ground away, ejected, or fallen into the stars over billions of years. Whatever worlds might have begun forming around Alpha Centauri A or B during the early history of the system were likely destroyed or ejected before they could reach significant size. Perhaps some small rocky bodies formed briefly, bodies the size of Earth's moon or Mercury, but even these failed to survive the continuous gravitational harassment from the binary companion. The habitable zones around both stars have been swept clean of the raw materials that planets require for construction, over billions of years of continuous grinding collisions and gravitational perturbations. Even if gravitational conditions somehow miraculously permitted stable orbits in these habitable zone regions, which the simulations tell us they don't, nothing remains from which to build worlds. You need raw materials to build planets. You need silicate dust to make rocky cores. You need ice to deliver water. You need gas to form atmospheres. The habitable zones of Alpha Centauri A and B have been emptied of these materials over billions of years of destructive processes. The situation around Alpha Centauri B appears even more dire than around Alpha Centauri A. This smaller, cooler star requires planets to orbit relatively close to receive adequate warmth for liquid water. The habitable zone around Alpha Centauri B lies between roughly half an astronomical unit and 1 astronomical unit from the star, closer than Earth's orbit around our Sun because the star is dimmer. At these relatively close distances, the gravitational perturbations from Alpha Centauri A during its closest approaches would destabilize planetary orbits on timescales of just millions of years, far shorter than the billions of years required for life to emerge and evolve into complex forms. Even if a planet somehow formed in Alpha Centauri B's habitable zone, even if all the previous difficulties were somehow overcome, it wouldn't remain in that stable orbit long enough for biological evolution to proceed beyond, perhaps, simple bacterial stages. Life on Earth required roughly 500 million years to emerge from non-living chemistry, then another 3.5 billion years to evolve from simple bacteria into complex animals. Intelligence appeared only in the last few million years of this 4 billion year evolutionary trajectory. any habitable planet must maintain stable conditions over comparable timescales for life to have reasonable probability of emerging, persisting, and evolving complexity. The orbital stability calculations for hypothetical planets in Alpha Centauri b's habitable zone show that even initially circular orbits in this region persist for only millions of years before gravitational perturbations accumulate to the point of catastrophic instability. The planet might survive a few thousand orbits of the binary system, a few 100,000 years, maybe even a few million years in fortunate configurations, but not billions of years, not long enough for multicellular life to evolve, let alone intelligence. Eventually, the accumulated perturbations either eject the planet from the system entirely, flinging it into interstellar space as a rogue world drifting through the galaxy without a star, or send it spiraling inward to plunge into its star in a final death dive. Either fate ends any possibility of hosting life. A few exceptionally lucky configurations in simulations might survive longer, perhaps tens of millions of years, but even that extended timescale falls far short of what life requires, so we're left with a comprehensively devastating picture. The nearest star system to Earth, the stellar neighbour we dreamed of reaching, turns out to be fundamentally hostile to planetary habitability through multiple independent mechanisms. Proxima Centauri, with its potentially habitable planet Proxima b, produces such extreme stellar violence that any planet in its habitable zone gets stripped of its atmosphere and sterilized by radiation. Alpha Centauri A and B, the Sun-like stars we hoped would offer better prospects, exist in a binary configuration that prevented stable planet formation in their habitable zones and would destabilize planetary orbits even if planets somehow existed. Every potential pathway to habitability in the Alpha Centauri system is blocked by fundamental physical processes. It's not bad luck. It's not unfortunate timing. It's the inevitable consequence of stellar properties and system architecture, and these problems aren't unique to Alpha Centauri. They apply throughout the galaxy wherever similar stellar types and configurations exist. This realization forces a complete reconceptualization of where life can exist in the universe. 70% of stars are red dwarfs with violent radiation environments. Roughly half of Sun-like stars exist in binary or multiple star configurations, many with separations that disrupt planet formation or destabilize orbits. When you eliminate the red dwarfs and the problematic binaries, you're left with perhaps 15% of stars that even potentially could host habitable worlds in stable orbits for billions of years. 15% sounds like a reasonable fraction until you factor in all the additional requirements. Not every system, even in this favourable 15%, will successfully form terrestrial planets. Some will form only gas giants. Some will form planets that are too small to retain atmospheres. Some will have planets that form at the wrong distances, outside or inside the habitable zones. The fraction that produces Earth-sized planets in long-term stable orbits in habitable zones around single Sun-like stars shrinks rapidly towards single-digit percentages of all stars. And that's before we even consider whether such planets maintain habitability over billions of years through geological activity, whether they retain water and atmospheres, whether life actually emerges, whether that life evolves, complexity, whether intelligence develops. Each additional requirement filters the candidate pool further. The final number of genuinely inhabited worlds in the galaxy might be not billions as optimists once projected, but thousands or tens of thousands, or possibly even fewer. If habitable worlds are genuinely rare, scattered sparsely across vast galactic distances rather than being common around most stars, then the implications for humanity's cosmic isolation become profound and disturbing. The Fermi Paradox, the question of why we haven't detected any evidence of extraterrestrial civilizations despite the apparently vast number of stars, might not be particularly paradoxical after all. The resolution could be straightforward and stark. We haven't detected alien civilizations because they're so rare and so widely separated that none exist close enough for us to detect with our current technology. The nearest technological civilization might be not hundreds of light years away, but thousands of light years distant, perhaps in some other spiral arm of the galaxy, too far for meaningful communication even if they're broadcasting. The silence we've observed through decades of searching with increasingly sensitive radio telescopes, the complete absence of any artificial signals from space, might simply reflect this fundamental isolation imposed by the rarity of habitable worlds. We're listening to empty sky because the voices we hope to hear originate too far away for us to detect them above the background noise of natural astrophysical sources. This interpretation challenges comfortable assumptions we've made about our cosmic context. For decades, since the first exoplanets were discovered in the 1990s, and the field of exoplanet science exploded with thousands of planetary detections, we've assumed that planets are common, that habitable zones exist around most stars, that life probably arose independently many times throughout the galaxy. The sheer numbers seem to demand abundant life. 400 billion stars in the Milky Way alone. Most of those stars hosting planets based on statistical surveys. Many of those planets orbiting at distances where temperatures might permit liquid water. Surely life must have emerged on thousands or millions or even billions of these worlds. Surely some fraction developed intelligence and technology. Surely we're not alone. But the Alpha Centauri findings inject harsh reality into these optimistic projections. Most stars can't host habitable planets. Most planetary systems don't form Earth-sized worlds in stable orbits in habitable zones. The conjunction of favourable circumstances required for genuine long-term habitability appears to be genuinely rare rather than common. Earth orbits a stable solitary star of the right type. That alone makes us unusual. Our planet formed at the right distance and has maintained a stable orbit for over 4 billion years. That's fortunate. We retained our water and atmosphere over geological timescales. That required geological activity and a protective magnetic field. We avoided catastrophic impacts and mass extinctions severe enough to completely sterilize the planet. That was lucky. Every step along the chain from stellar properties to system architecture to planet formation to long-term stability to life's emergence represents a filter that eliminates most candidates. When you multiply many small fractions together, fractions like 1 in 10 or 1 in 20 for each step, you get very small final numbers. Maybe genuinely habitable worlds comprise not 1 in 1,000 stars, but 1 in 1,000,000 stars or even rarer. 1 in 1,000,000 sounds impossibly rare until you remember there are 400 billion stars in our galaxy. 1 in 1,000,000 still yields 400,000 habitable worlds spread across the Milky Way. That still sounds like a lot until you consider the distances involved. The galaxy spans 100,000 light-years. 400,000 worlds spread across that volume means average separations of perhaps 10 to 20 light-years between neighbouring habitable systems, and that's if they're evenly distributed, which they almost certainly aren't. Real habitable worlds would cluster in galactic regions with favourable characteristics, leaving vast voids where no habitable planets exist at all. The actual nearest habitable world to Earth could easily be 50 or 100 light-years away, rather than the mere 4.2 light-years to Alpha Centauri. A journey of 100 light-years at 20% light speed, the velocity proposed for Breakthrough Starshot would require 500 years. 500 years of travel time plus 100 years for signals to return makes a 600-year mission from launch to data reception. 24 generations would live and die before the first images arrived back at Earth. The civilization that launched the mission would be separated by a vast gulf of time from the civilization that receives the results. Languages might evolve. Political systems might transform completely. The entire context of human society could change beyond recognition during such a mission. And that's just for an uncrewed flyby probe travelling at relativistic speed, using speculative propulsion technology we don't yet have. Physical travel by humans to nearby, habitable worlds becomes effectively impossible using any technology consistent with known physics. Even travelling at 10% of light speed, which would require enormous energy investment and isn't achievable with any propulsion system we currently possess or can envision building in the near future. A journey of 100 light-years would last 1,000 years. 1,000 years. 40 generations would live and die aboard the vessel before arrival at the destination. The travellers reaching the target planet would be separated by such enormous cultural and temporal distance from the people who launched the mission that they might as well be a different species. They would have no personal connection to Earth, no memory of its landscapes or cultures beyond historical records. They would be natives of the ship, born and raised in an artificial environment, arriving finally at an alien world they must somehow colonize and make home. This is the stark reality the Alpha Centauri observations force us to confront. Our nearest stellar neighbours cannot host life and cannot serve as destinations for humanity's first interstellar journeys. The truly habitable worlds, if they exist at all within reach, lie far more distant than we hoped, separated by gulfs of space that render travel effectively impossible and communication painfully slow. We are cosmically isolated not merely by distance, but by the fundamental rarity of planets where life can emerge and persist. We might share the galaxy with other conscious beings, but remain completely unable to communicate with them, or learn from them, or gain any benefit from knowing they exist. Each civilization develops alone, experiences its own triumphs and tragedies, accumulates its own knowledge, faces its own challenges, with no help available from distant cosmic neighbours who remain forever unreachable. This isolation carries philosophical implications that weigh heavily. If Earth represents one of perhaps thousands or tens of thousands of inhabited worlds scattered across a galaxy 100,000 light-years in diameter, if the nearest life-bearing planet sits 100 or 200 or 500 light-years away too far for meaningful contact, then what happens here on Earth takes on cosmic significance that previous generations couldn't have imagined. We're not one civilization among millions who could continue evolving if we destroy ourselves. We might be one of a handful scattered so widely that each evolves in complete isolation. What we create, what we learn, what we accomplish exists nowhere else within reach. If we extinguish ourselves through war or environmental collapse, that accumulated knowledge and culture disappears from the universe, or at least from this corner of it, rather than merely from one location among many. The responsibility this implies is staggering in its weight. The decisions we make about environmental protection, about weapons proliferation, about social stability and cooperation, about preserving our biosphere and technological infrastructure, these aren't just local decisions affecting one planet among countless others. They might be existentially important decisions affecting one of very few inhabited worlds that exist anywhere in this region of the galaxy. We didn't ask for this responsibility. Most people would probably prefer to imagine a universe teeming with life that continues existing regardless of what happens on Earth. But the evidence, particularly the detailed observations James Webb has provided of our nearest stellar neighbours, increasingly suggests that such comforting assumptions reflect wishful thinking rather than accurate assessment of cosmic reality. The universe is not arranged for our psychological comfort. It's governed by physical laws indifferent to biological requirements or human hopes. Those physical laws have produced a cosmos where habitable worlds appear to be genuinely rare, where the conjunctions of favourable circumstances required for life occur infrequently, where intelligent technological civilizations might be separated by distances that preclude any meaningful interaction. The silence from Alpha Centauri, the absence of any habitable worlds or biological signals from our nearest stellar neighbours, provides a small but significant data point supporting this darker view of cosmic rarity. The nearest place we might hope to find life offers only sterile rocks, orbiting violent or gravitationally chaotic stars. If the immediate cosmic neighbourhood is this inhospitable, what reason do we have to think the rest of the galaxy is fundamentally different? Perhaps instead of imagining inevitable alien contact and cosmic community, we should prepare mentally for permanent cosmic isolation. Perhaps instead of expecting to find neighbours among the stars, we should accept responsibility as possibly the only conscious observers in this region of space, the only voices, the only minds contemplating the universe's mysteries from this particular corner of the cosmos. That acceptance doesn't mean abandoning the search for life elsewhere, or giving up hope of eventually finding evidence of other civilizations. The universe is vast and our knowledge remains limited. New discoveries could challenge current understanding. Future observations might reveal habitable worlds that we can't yet detect. The possibility remains open, even as the probability seems to diminish with each new finding. But the Alpha Centauri observations deliver a message we cannot ignore. Our nearest cosmic neighbours are dead worlds, incapable of hosting life, offering no sanctuary for future human expansion, providing no evidence that habitable planets are common or easy to find. Whatever life exists elsewhere hides beyond our current observational capabilities, beyond our current reach, perhaps beyond any future reach using technologies consistent with known physics. We are alone, genuinely and perhaps permanently alone, in ways that previous generations with their optimistic assumptions about abundant habitable worlds could not have fully appreciated. The golden mirrors of James Webb have shown us this harsh truth. The cosmos is beautiful, magnificent in its scale and complexity, but it's also fundamentally inhospitable to life in most places, hostile to the complex chemistry that biology requires, indifferent to whether consciousness exists or extinguishes itself. Earth is not merely one comfortable world among billions where we could relocate if necessary. It's a rare oasis in a desert that stretches across light years in every direction. The stars that beckon from the night sky cannot provide refuge. They cannot host our descendants. They cannot answer our questions about whether life exists elsewhere. They can only shine mutely, beautiful but barren, magnificent but meaningless for biological purposes. The James Webb observations of Alpha Centauri represent a watershed moment in human understanding of our cosmic context. We gazed at our nearest stellar neighbours with hope, with dreams of habitable worlds and possible life, with visions of humanity's first steps toward becoming an interstellar species. We received instead a lesson in cosmic inhospitality, a demonstration that proximity doesn't guarantee promise, a revelation that hope and reality often fail to align. Proxima b exists as a radiation-scorched wasteland stripped of any atmosphere it might once have possessed. Alpha Centauri, A and B, orbit each other in a configuration that prevented stable planets from forming where life might have emerged. The entire nearest stellar system to Earth offers nothing but confirmation of how special and rare Earth's habitability truly is. This knowledge should inspire in us a profound sense of responsibility. If habitable worlds are as rare as these observations suggest, then Earth might be the only planet hosting life that's accessible to us in any meaningful time frame. The choices we make about environmental protection aren't just local decisions. They're decisions that might determine whether life at this level of complexity and consciousness continues existing in this part of the galaxy, or disappears entirely. The universe has taught us a harsh lesson through these observations, but perhaps it's a lesson we needed to learn. We are not guaranteed cosmic community. We are not assured of refuge elsewhere if we make Earth uninhabitable. We have this one precious world, this singular example of a planet where conditions aligned favourably enough for life to emerge and flourish. What we do with that opportunity, whether we preserve and nurture it or squander and destroy it, might be the most cosmically significant decision we ever make as a species. Despite these sobering realizations about Alpha Centauri's inhospitability and the broader implications for galactic habitability, the search for life beyond Earth continues undeterred. Scientists haven't abandoned hope of discovering life elsewhere, but expectations have been substantially and appropriately recalibrated based on mounting evidence about how genuinely rare habitable conditions might actually be throughout our galaxy and the universe beyond. The search for extraterrestrial intelligence, universally known by its acronym SETI, began formally in 1960 when astronomer Frank Drake pointed the 85-foot Tittel radio telescope at Greenbank, West Virginia, toward two nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened for artificial signals that might indicate the presence of technological civilizations. That pioneering search, called Project Ozma after the Queen in L. Frank Baum's Oz books, detected nothing but natural radio noise from the stars themselves. The search has expanded enormously in scope and technological sophistication since those humble beginnings, over 6 decades ago. Modern SETI programs operated by organizations like the SETI Institute in Mountain View, California, and Breakthrough Listen, funded by tech billionaire Yuri Milner, monitor millions of frequencies simultaneously across large portions of the sky using some of Earth's largest and most sensitive radio telescopes. Computers analyze incoming data streams in real time for patterns that might indicate artificial origin, distinguishing deliberate transmissions from natural radio emissions produced by stars, pulsars spinning, neutron stars emitting lighthouse-like beams, and other astrophysical sources. The search has examined hundreds of millions of star systems across multiple wavelength ranges, from long-wave radio up through optical light where laser signals might be transmitted, using detection algorithms capable of recognizing signals far weaker than anything human technology currently produces or broadcasts into space. The result after 6 decades of increasingly sophisticated searching using progressively more sensitive instruments and more comprehensive search strategies is stark and undeniable. Nothing, not a single confirmed detection of artificial extraterrestrial signals, no narrowband radio transmissions that couldn't be explained as terrestrial interference or natural astrophysical phenomena, no optical laser pulses carrying encoded information, no evidence whatsoever of technological civilizations broadcasting into space from any of the hundreds of millions of star systems that have been monitored. The silence remains unbroken despite our best efforts, despite dedicating thousands of hours of telescope time on the world's premier radio astronomy facilities, despite analysing petabytes of data using increasingly sophisticated signal processing algorithms, despite searching at wavelengths from meters down to nanometers across the electromagnetic spectrum. We've looked and listened with ever-improving tools and found nothing that suggests we have cosmic companions anywhere within detection range. This null result, this comprehensive absence of detected signals, can be interpreted in multiple different ways that lead to very different conclusions about what it means. Perhaps we're searching incorrectly, looking at the wrong frequencies or for the wrong types of signals that alien civilizations don't actually use for communication. Maybe extraterrestrial civilizations employ communication methods we haven't thought of, using quantum entanglement or neutrino beams or gravitational waves or techniques completely unknown to current human physics. Perhaps civilizations broadcast only briefly during a short window of their technological development, before transitioning to communication methods we cannot detect with our current instruments. Maybe there's a natural progression where species first use radio, then move to optical lasers, then adopt something beyond our current technological capabilities, and the window, when civilizations use methods we can detect, lasts only a few centuries. If we're only now entering that window and other civilizations have already moved beyond it, we'd miss each other's signals entirely. Perhaps signals exist but remain too weak for even our most sensitive current instruments to detect above the background noise of natural radio sources in the galaxy. The inverse square law means that signals weaken dramatically with distance. A transmission from thousands of light years away might fall below our detection threshold, even if it was quite powerful at its source. Future instruments with greater sensitivity or larger collecting areas might detect signals that current telescopes miss. But the Alpha Centauri observations, combined with broader evidence about stellar violence and binary disruption and atmospheric loss mechanisms, suggest a more fundamental and disturbing explanation for the silence. There may be very few civilizations to detect anywhere within signaling range of Earth. If habitable worlds are genuinely rare rather than common, if they exist around only a small fraction of stars rather than most stars, if they're separated by hundreds or thousands of light years rather than tens of light years, then the nearest technological civilization might lie so far away that we can't detect their signals even with our best instruments. Signals from civilizations thousands of light years distant would be extraordinarily weak after spreading out across such enormous distances. They'd be diluted to a whisper barely distinguishable from the cosmic microwave background, from the faint radio glow of distant galaxies, from the collective radio noise of countless natural astrophysical sources. Detecting such weak signals would require telescope arrays spanning continents with sensitivity exceeding anything we currently operate by many orders of magnitude. The silence we've observed through decades of dedicated searching with increasingly capable instruments might not reflect our technological inadequacy or incorrect assumptions about communication methods. It might simply and starkly reflect the fundamental isolation imposed by habitability rarity throughout our galaxy. If genuinely habitable worlds exist around only one star in a million, if technological civilizations arise on only 1 in a million habitable worlds, then the nearest civilization might be 10,000 light years away or even farther. At such distances, communication becomes essentially meaningless, even if we could detect their signals and they could detect ours. A message transmitted today wouldn't arrive for 10,000 years. The civilization that sent it might have gone extinct by the time it arrives. A reply sent back wouldn't return for another 10,000 years. 20,000 years round trip for a single exchange of hello. Human civilization, recorded human history stretches back only about 6,000 years. 20,000 years ago, humans hadn't yet developed agriculture. We lived as hunter-gatherers in small bands. We had no writing, no permanent settlements, no technology beyond stone tools and fire. Imagine trying to maintain institutional continuity across such a vast time span. The civilization that receives a reply to a message we sent today would be as different from us as we are from Paleolithic hunter-gatherers. Meaningful dialogue, genuine communication, requires exchange rates compatible with the lifespans of the participants. You need to be able to ask a question and receive an answer while you're still alive and while the social context that made the question meaningful still exists. 20,000-year lags make dialogue impossible. The best you can achieve is one-way broadcasts into the void, messages in bottles cast into an ocean of space and time, with no real hope of reply or mutual understanding. SETI programs continue despite these daunting realizations, understanding that even extraordinarily low probability of detection justifies the search given the profound implications of success. Discovering even one extraterrestrial signal, even one confirmed artificial transmission from beyond our solar system, would transform human understanding of our cosmic context overnight. It would prove we're not alone. It would demonstrate that life and intelligence can arise elsewhere. It would provide a data point suggesting the universe might be less sterile than Alpha Centauri makes it appear. The search costs relatively little compared to its potential philosophical and scientific payoff. Radio telescopes can search for signals simultaneously with their normal astronomical observations. The marginal cost of running CT programs is modest, requiring mainly computer processing to analyze data that the telescopes collect anyway for other scientific purposes. Given the enormous importance of the question and the relatively low resource requirements, continuing the search makes sense even with appropriately modest expectations about near-term success. Radio astronomy facilities like the Allen Telescope Array, operated by the SETI Institute in Hat Creek, California, the Greenbank Telescope in West Virginia, the Parkes Observatory in Australia, and the Meerkat Array in South Africa, continue monitoring the sky systematically for artificial signals. The breakthrough. Listen Initiative provides substantial funding for extensive CT observations, using some of Earth's most powerful and sensitive radio telescopes, devoting thousands of hours of telescope time to comprehensive sky surveys. The search examines millions of star systems, prioritizing those that appear most likely to host habitable planets based on available data about stellar types, ages, metallicities, and known exoplanets. Single sun-like stars at appropriate ages with confirmed terrestrial planets in their habitable zones receive particular attention. But the search also surveys broader regions more randomly, understanding that our assumptions about which stars are most promising might be wrong. But even the term most likely to host habitable planets doesn't mean likely in absolute terms. A star system with 1% probability of hosting an inhabited world, which would make it one of the very best candidates we can identify based on current knowledge, still implies 99% probability of finding nothing there. The odds remain strongly against success for any individual target system. When searching across millions of such systems, the cumulative probability of detecting something does increase substantially. If you examine 1 million systems each with 1 in a million chance of hosting a detectable civilization, probability theory suggests you might find one positive detection, but that's still just probability, not certainty. You might find 0, you might find 3. The search must continue across enormous numbers of targets with appropriate patience and realistic expectations. The question demands answering regardless of how difficult the answer proves to obtain. Are we alone in the universe, genuinely singular in a cosmos that seems to offer infinite opportunity for biology to arise? Or does life exist elsewhere, perhaps rarely but meaningfully, providing cosmic companionship even if separated by distances that preclude physical contact? These represent some of the most profound inquiries humanity can pursue, questions that strike at the heart of what it means to be human and how we fit into the broader cosmic context. The philosophical importance of these questions justifies continued investment in seeking answers, even when success seems increasingly uncertain based on accumulating evidence. We need to know, even if the answer is disappointing, even if the answer confirms our isolation rather than providing cosmic community. Knowledge of truth, however uncomfortable or disturbing, serves humanity better than comfortable illusions maintained through willful ignorance. James Webb Space Telescope will continue peering into the cosmos with its golden mirrors, collecting ancient photons from across the universe. conducting observations that progressively refine our cosmic census of habitability and our understanding of where life might or might not exist. The telescope has enough propellant for at least another decade of operations, possibly longer with careful management of remaining reserves. Each observation adds incremental knowledge even when results confirm absence rather than revealing presence. The telescope has begun systematic surveys of other nearby red dwarfs beyond Proxima Centauri, searching for atmospheric signatures around confirmed exoplanets orbiting these dim stars. Early results from these surveys reinforce rather than contradict the Proxima Centauri findings. Red dwarf planets examined so far consistently show minimal atmospheric signatures, suggesting widespread atmospheric loss consistent with intense stellar activity stripping atmospheres faster than geological processes can replenish them. Every additional red dwarf planetary system examined provides another data point confirming the pattern. The violence isn't unique to Proxima Centauri. It characterizes red dwarfs throughout the galaxy. The atmospheric stripping isn't an anomaly. It's the expected outcome when planets orbit close enough to receive habitable temperatures from dim stars whose magnetic activity produces devastating flare events. Surveys of binary star systems with various orbital configurations will help determine more precisely which separation ranges permit stable planet formation in habitable zones, and which separations prove too disruptive for planets to form or maintain long-term orbital stability. Preliminary data indicates that the problematic separation range exemplified by Alpha Centauri A and B extends across a broader range than initially expected, potentially excluding even more binary systems from habitability consideration than worst-case models predicted. The observations progressively constrain the fraction of stars capable of hosting truly habitable worlds. Each new constraint, each additional observation, each refinement of our understanding tends to reduce rather than expand this fraction. The trend is unmistakable and unambiguous. Habitability appears to demand a fortunate conjunction of favourable circumstances that occurs less frequently than optimistic early estimates, projected based on incomplete information. The universe operates according to physical laws indifferent to human hopes about cosmic companionship. Those laws have produced a cosmos where stellar violence destroys atmospheres, where binary perturbations prevent planet formation, where tidal forces lock planets into configurations hostile to life, where radiation strips away water and organic molecules. The requirements for habitability are stringent, and the pathways to meeting those requirements are narrow and easily blocked. Future observations might identify promising candidates for follow-up study, individual star systems that appear to have avoided the various pitfalls that plague Alpha Centauri and most other nearby stars. Single sun-like stars at appropriate ages with confirmed terrestrial planets detected in their habitable zones through transit observations or radial velocity measurements would represent high-priority targets for detailed atmospheric characterization using James Webb's unprecedented spectroscopic capabilities. Detection of water vapor in a planet's atmosphere would indicate the presence of the universal solvent necessary for biochemistry as we understand it. Detection of oxygen in substantial quantities might suggest photosynthetic processes, though oxygen can be produced through non-biological photochemical processes as well, so this isn't definitive. Detection of methane in the presence of oxygen would be particularly interesting, because these gases react with each other and don't naturally coexist without continuous replenishment from some active source, potentially biological metabolism. Such biosignature detections would justify enormous investment in more detailed study, in longer observation campaigns, in dedicated space missions to study these systems. They would provide the strongest evidence short of receiving actual radio transmissions that life exists beyond Earth, that biology arose independently elsewhere, that Earth isn't unique. But based on current data trends and the Alpha Centauri observations, such promising systems will likely prove rare rather than common, scattered widely across the galaxy rather than clustering in our immediate neighbourhood. Most star systems examined in detail will probably reveal similar or different but equally fatal challenges to hosting life. Alpha Centauri demonstrated that proximity and initial promise don't guarantee habitability when we examine systems carefully with sensitive instruments. Most nearby stars face comparable problems or unique problems that produce similarly uninhabitable outcomes. the galaxy likely contains far fewer genuinely habitable worlds than early exoplanet enthusiasm and optimistic statistical projections suggested before we had detailed data. James Webb might operate for another decade or longer, collecting data that progressively refines our cosmic sensors of habitable worlds. Future space telescopes with even greater capabilities are planned, though budget uncertainties and political changes cloud their timelines and whether they'll actually be funded and launched. Ground-based extremely large telescopes now under construction, massive facilities with mirrors 30 or 40 meters in diameter, will complement space-based observations by providing additional data on exoplanet atmospheres and stellar characteristics. The technological capability to study worlds around nearby stars in unprecedented detail will continue improving over coming decades. What we cannot yet determine with certainty is whether improved capabilities will discover habitable worlds among the stars, finally revealing those oases in the cosmic desert we hope exist, or whether they'll merely confirm with increasing precision and mounting detail that such worlds are genuinely rare, scarce beyond what optimists imagined possible. Current trends based on accumulating observations suggest the latter outcome is more probable than the former, but science requires following evidence wherever. It leads regardless of whether conclusions align with our preferences or comfort our fears. We must look because we must know, even if knowing proves disappointing, even if truth contradicts hope. Perhaps the most valuable lesson the Alpha Centauri observations provide isn't about distant stars but about our own planet Earth. By revealing the hostility of nearby stellar neighbourhoods through detailed measurements rather than speculation, these observations cast Earth's habitability in sharper relief than any previous discoveries or theoretical arguments could achieve. Earth isn't merely one habitable planet among countless others scattered throughout the galaxy, like grains of sand on an infinite beach. It's potentially a genuinely rare example of conditions aligning favourably enough, circumstances coinciding propitiously enough, for life to not only emerge from non-living chemistry, but to persist through billions of years of continuous evolution and eventually produce complex forms, including intelligence and technological civilization. The chain of circumstances that created Earth's long-term habitability didn't arise through cosmic inevitability or universal abundance. It emerged through a remarkable conjunction of favourable factors that might be genuinely uncommon in the broader galactic context. Our distance from the Sun, placing us in a stable location within the habitable zone, neither too close nor too far, allowing liquid water to exist on our surface throughout most of Earth's history. Our planet's mass and composition, large enough to retain an atmosphere through gravitational binding, but not so large that we became a gas giant, with just the right balance of rocky material and volatile compounds delivered by asteroids and comets during our formation. Our magnetic field generated by convection in our liquid iron core, deflecting solar wind particles that would otherwise gradually strip our atmosphere into space over geological timescales. Our atmospheric chemistry, particularly the ozone layer that protects us from harmful ultraviolet radiation, allowing life to colonize land surfaces after spending billions of years evolving in protected ocean depths. Our moon's stabilizing influence on Earth's rotational axis, preventing wild swings in axial tilt that would produce extreme seasonal variations potentially hostile to complex life requiring stable climate patterns. Jupiter's protective role, gravitationally deflecting many comets and asteroids that might otherwise impact Earth with potentially catastrophic consequences for life, reducing the impact rate to something survivable rather than continuously catastrophic. Our star's stability, producing steady, predictable output without the violent flare events that characterize red dwarfs, providing consistent warmth and light that has remained relatively constant for over 4 billion years. Our location in the galaxy, in the Milky Way's habitable zone at the right distance from the galactic centre, where heavy element abundances are sufficient for rocky planet formation, but stellar densities are low enough that close encounters with other stars or supernova explosions remain rare. Each of these favourable circumstances could have been otherwise. Small changes in any of these factors might have rendered Earth uninhabitable, or at least inhospitable to complex life. Together they created conditions where biology not only emerged, but persisted through numerous mass extinctions and environmental catastrophes, eventually evolving into the rich biosphere we observe today, with millions of species adapted to nearly every environment Earth offers. The Alpha, Centauri findings emphasize how fortunate this conjunction was by demonstrating through direct observation rather than speculation how easily things could have been completely different. If Earth had formed around a red dwarf instead of a sun-like star, stellar radiation would likely have stripped our atmosphere and sterilized our surface as it did to Proxima b. If our Sun had a close binary companion like Alpha Centauri A and B do, gravitational perturbations might have prevented Earth from forming in the first place, or thrown us into an unstable eccentric orbit unsuitable for long-term habitability. If any of dozens of other crucial factors had been slightly different from what they turned out to be, we wouldn't exist to contemplate these questions. We're here, conscious and capable of understanding our cosmic context, only because an improbable sequence of favourable circumstances happened to coincide. That recognition should inspire profound appreciation for the world we inhabit, and sobering awareness of our responsibility as its only technological species. We cannot assume other habitable worlds exist nearby enough or in sufficient numbers to serve as alternatives if we make Earth uninhabitable through environmental destruction, nuclear war, or other preventable catastrophes that lie within human capacity to cause. The universe has shown us through the Alpha Centauri observations that it doesn't provide spare planets conveniently located for our use, that habitability is rare rather than common, that we might have nowhere else to go if we ruin this world through carelessness or conflict. The environmental challenges facing Earth, including climate change driven by greenhouse gas emissions, biodiversity loss from habitat destruction and pollution, resource depletion from unsustainable consumption patterns, ocean acidification and plastic contamination, all of these take on additional weight and urgency in this cosmic context. These aren't merely local problems affecting one planet among countless others, where the damage might not matter in the grand scheme. They potentially threaten the only known example of complex life in the entire accessible cosmos, or at minimum one of a very small number of such examples separated by impossible distances. We're not damaging one garden among millions. We might be damaging the only garden that exists anywhere within thousands of light years, the only place where life arose and flourished into the magnificent complexity we see in Earth's biosphere. Previous generations could perhaps be forgiven for treating Earth carelessly, under the assumption that the universe teemed with habitable worlds, that life was common throughout the cosmos, that human expansion into space would eventually provide alternatives to our homeworld. Science fiction visions of easy space travel and abundant habitable planets shaped expectations. Optimistic projections about billions of Earth-like worlds throughout the galaxy encouraged assumptions that we had options, that Earth was replaceable if necessary. We no longer have that excuse. The evidence increasingly suggests that Earth represents something genuinely precious and potentially irreplaceable. A cosmic oasis in a vast desert of sterile worlds orbiting violent stars in chaotic gravitational configurations. The detailed observations made possible by James Webb and other modern astronomical instruments have replaced speculation with measurement, hope with reality, comfortable assumptions with uncomfortable truths. This doesn't mean we should abandon hopes of eventually expanding into space or continuing to search for life elsewhere among the stars, but it does mean we cannot justify present environmental destruction based on hypothetical future alternatives that might not actually exist or might lie so far away as to be completely inaccessible. The planet we have right now, the world we evolved on and adapted to, might be the only habitable world accessible to humanity for the foreseeable future, potentially for the entire future of our species. Learning to live sustainably on Earth isn't merely an environmental nicety or political preference. It's a cosmic imperative if we want the remarkable phenomenon of human consciousness and civilization to persist into the deep future rather than extinguishing itself through preventable catastrophe within the next few centuries. There may genuinely be nowhere else to go, no backup planet waiting in reserve, no alternative world we can flee to if we make Earth uninhabitable. The silence from Alpha Centauri, the dead worlds orbiting violent and chaotic stars, the absence of habitable planets in our immediate cosmic neighbourhood, these findings should inspire us to protect and preserve what we have, rather than carelessly assuming the universe will provide alternatives. We are cosmically isolated and potentially cosmically precious, possibly the only conscious observers in this vast region of space and time, the only minds contemplating existence and meaning against the backdrop of an overwhelmingly unconscious universe. This realization carries philosophical and even spiritual weight regardless of one's religious or metaphysical beliefs. Whether you view human existence as a cosmic accident or divine creation or something between those extremes, the rarity and apparent uniqueness of our situation demands acknowledgement. We are not guaranteed companionship among the stars. We are not assured of rescue or refuge if we fail here. What we do on Earth, how we treat this world and each other, might represent the only experiment in consciousness and civilization occurring anywhere in this corner of the galaxy. The golden mirrors of James Webb have shown us the universe as it actually is rather than as we wish it to be. That view is simultaneously harsh and beautiful, isolating and clarifying, disturbing and strangely focusing. The nearest stars shine bright and beautiful in our skies, but offer no sanctuary for life, no homes for biology, no refuge for consciousness. They burn as sterile nuclear furnaces in the cosmic night, magnificent in their energy output but meaningless for biological purposes. Somewhere in the vast reaches of space beyond what we can currently observe or reach, answers about whether other life exists await discovery by observers we cannot yet identify using instruments we cannot yet imagine. Perhaps someday, centuries or millennia in our future, if we survive that long, humanity will develop capabilities that allow us to explore beyond our immediate neighbourhood, to reach the truly habitable worlds if they exist, to make contact with whatever life might have arisen elsewhere. Until that distant hypothetical future, we wait on Earth. We listen to silence from the stars, we wonder about our cosmic solitude, and we confront the disturbing truth about Alpha Centauri. Our nearest stellar neighbours prove to be a graveyard rather than a gateway to the stars, dead worlds rather than living oases, cosmic tombstones marking the spots where habitability failed, rather than signposts pointing toward cosmic community. The James Webb observations delivered not the confirmation we sought, but the truth we needed, however uncomfortable that truth might be. We are more alone than we hoped, more isolated than we imagined, more responsible for our own survival than we wanted to believe. The universe has taught us this lesson through cold measurement and careful observation. Now we must decide what we do with this knowledge and whether we rise to meet the responsibility it implies, or fail to recognize the cosmic significance of the choices we make here on this rare, precious world we call home. The story of Alpha Centauri is not over. Observations will continue. New instruments will examine these stars with ever greater precision. Our understanding will refine further as technology improves, and observation campaigns accumulate more data. But the fundamental conclusion seems unlikely to change. The nearest stars cannot host life as we know it. They offer no refuge, no companionship, no evidence that the universe treats biology with any special consideration. For 60 years we gazed at Alpha Centauri and saw hope. We imagined worlds where life might flourish, neighbours we might one day contact, destinations for humanity's first interstellar voyages. James Webb Space Telescope turned those dreams to dust. The golden mirrors reflected back a harsh truth about cosmic isolation and the genuine rarity of planets capable of hosting life over billions of years. What we learned from studying our nearest stellar neighbours changes everything about how we must think about Earth's value and our cosmic responsibilities. The silence from Alpha Centauri echoes across 4 light-years of empty space, a silence that might extend for hundreds or thousands of light-years in every direction we look. We are alone, perhaps not absolutely alone in the entire universe, but functionally alone in any meaningful sense. And in that aloneness, in that cosmic isolation revealed through careful scientific observation of our nearest neighbours, we find not despair, but purpose. If Earth is genuinely precious, genuinely rare, genuinely irreplaceable, then preserving it becomes not just a local concern but a cosmic imperative. That is the disturbing but clarifying truth that James Webb recently found in Alpha Centauri.